Today, we're focusing on the seawater reverse osmosis, or SWRO, makeup water supply system designed specifically for a liquid-cooled data center located in the Batam Island and Nongsa Coastal Industrial Estate. This concept integrates direct-to-chip liquid cooling with traditional cooling towers and advanced SWRO desalination technology. We'll dive into important aspects such as water use efficiency and Tier 3 readiness, which are crucial for ensuring reliable and sustainable operations. This training is tailored for engineers and covers detailed calculations, equipment selection, redundancy strategies, and integrated control architectures. Overall, it's a comprehensive package aimed at optimizing water supply and cooling performance for high-demand coastal data centers. Let's begin with the executive summary, focused on the cooling tower water balance. Closed wet towers primarily protect the facility's loop, but don't significantly change evaporation rates when the heat duty stays the same. The real water saving comes from hybrid operation, which combines different cooling methods to optimize water use. The training concept covers several important elements, such as the Batam Coastal Data Center's water supply, seawater reverse osmosis desalination, direct liquid cooling, and how these integrate with cooling towers. Looking at the key conclusions, the total IT load is 144 megawatts, divided into 6 modules of 24 megawatts each. Direct liquid cooling handles 115.2 megawatts of that load, while the remaining heat is managed with chillers in the air path. Both open and closed wet cooling towers use almost the same amount of makeup water when rejecting equal amounts of heat. However, hybrid closed adiabatic systems reduce water consumption by cutting down the hours that wet cooling is needed. When we talk about peak day makeup water, open circuit wet towers and closed circuit wet towers require roughly 6,445 cubic meters per day. Hybrid systems optimize this significantly, with water use dropping to as low as 2,900 cubic meters per day when operating at 45% wet. Even with conservative 65% wet operation, water use is still considerably lower than pure wet tower setups. The water balance formula essentials break down into 3 parts: evaporation, blowdown, and makeup. Evaporation depends on the heat rejection, the density of water, and the latent heat of vaporization. Blowdown is calculated based on evaporation and the cycles of concentration in the system. Makeup water is the sum of evaporation, blowdown, and drift losses. In terms of system architecture, the reference chiller distribution units, or CDUs, are about 2.3 megawatts each. 60 of these units are installed across the 6 modules. Importantly, the IT secondary coolant is kept separate from the cooling tower's makeup water, and the seawater reverse osmosis system follows an N+1 redundancy approach to ensure reliability. Now, why doesn't closed wet cooling show a higher water usage? For a given heat rejection, the latent heat removal through evaporation is essentially constant. The presence of the coil affects tower size, approach temperature, and fan selection, but doesn't fundamentally change the evaporation load. Slight differences in makeup water come from assumptions about drift losses and cycles of concentration. Finally, the training takeaway emphasizes using open versus closed wet towers primarily for contamination control and ease of maintenance. When your goal is to reduce water usage effectiveness and enhance water security, the hybrid closed adiabatic approach is the best strategy to employ. This balances operational needs with sustainability objectives effectively. In this training, we will focus on several key objectives that engineers need to understand thoroughly. The training is designed as a comprehensive package covering design basis, calculations, and system integration. Our case study revolves around the Batam Coastal Data Center, specifically addressing its water supply, seawater reverse osmosis desalination, direct liquid cooling, and cooling tower integration. Technically, you'll learn how direct-to-chip liquid cooling impacts heat rejection and water demand. We'll dive deep into how to calculate critical parameters like CDU capacity, secondary coolant flow, facility water flow, chiller condenser water, and cooling tower capacity. Additionally, you'll understand the sizing of important components like seawater feed, brine management, desalination trains, tanks, and makeup water distribution. From an engineering perspective, we'll compare different cooling tower types, open wet, closed wet, and hybrid closed adiabatic towers, and uncover common misconceptions, particularly regarding water savings with closed-circuit towers. We'll also cover how to ensure your water systems align with important benchmarks and standards such as Water Use Effectiveness, WUE, LEED Green Mark, Uptime Institute Tier 3, and TIA 942 Rated 3. Finally, we'll provide clear decision-making guidance for choosing the appropriate cooling tower type based on specific priorities. If simplicity and initial cost are critical and water availability is secure, open wet towers are preferred. However, if protecting facilities' clean water loop and ensuring operational reliability are paramount, closed wet towers are the better choice. For cases where managing water risk, driving sustainability efforts, and coastal water source resilience are strategic, hybrid closed adiabatic towers offer the best solution. This framework will help you make informed decisions tailored to your project's needs. Now, let's walk through the structure of this training deck. It offers a comprehensive flow, starting from the coastal water source all the way to managing the heat removal in IT racks, along with strategies for environmental certification. The training concept package focuses on the Badham Coastal Data Center and covers critical elements such as a water supply from the sea, SWRO desalination, direct liquid cooling, and how cooling towers are integrated into the system. The deck is divided into 9 key sections. First, we provide the context for the Badham and Nongsa Coastal Data Center location. Next, we cover the design basis, including the 144 megawatts IT load and how the liquid cooling is split. Following that, we dive into detailed calculations involving the CDU, rack secondary loops, power distribution units, CRH/FW units, chillers, and pumps. Then, we explore different cooling tower alternatives, including open, closed, and hybrid adiabatic towers. The next section covers the water balance, makeup water demand, water usage efficiency, and sizing of the SWRO system. We then explain the SWRO process itself, along with brine and blowdown management and distribution of makeup water. Afterwards, the training addresses control systems, instrumentation, redundancy measures, and readiness for Tier or Rated 3 data center standards. We also include strategies for achieving environmental certifications like LEED, Green Mark, Uptime Institute, and TI 942. Finally, the deck concludes with a complete schematic overview, a training summary, and references to support continued learning. This structure ensures a holistic understanding of both the technical and environmental aspects of the data center cooling system. Now, we're focusing on Section 01, which covers a coastal site and design basis for our project. Specifically, we'll be looking at Badham Island and the Nongsa coastal context. This includes the environmental factors and baseload assumptions that we've used as a foundation for all our calculations throughout the design process. This section also introduces our training concept package, which integrates crucial systems like the water supply for Badham Coastal Data Center, seawater reverse osmosis desalination, direct liquid cooling, and cooling tower integration. Understanding these elements is key because they form the backbone of how we approach sustainable and efficient cooling solutions for the data center in this coastal environment. Let's take a closer look at the context of Badham and Nongsa as a key area for digital and data center growth, especially focusing on coastal water resilience. Nongsa is strategically positioned for expanding data infrastructure, making water supply and cooling systems critical to its operation. Our training concept package addresses the essential components here: the supply of water from the coastal environment, integration of seawater reverse osmosis, SWRO for desalination, direct liquid cooling for IT equipment, and the use of cooling towers. Why is Badham and Nongsa so important? First, its island and coastal setting places it close to Singapore and key regional interconnection routes, which are vital for data center connectivity. The rapid growth in high-density cloud and AI data centers significantly increases the demand for reliable cooling water and overall utility resilience. Being on the coast allows us to use seawater through SWRO, but this comes with challenges like marine permits, corrosion-resistant design, managing brine discharge, and ensuring resilience against storms. We evaluate SWRO because it offers a dedicated source of non-potable water for cooling towers, reducing reliance on municipal potable water, especially crucial during droughts or facility expansions. Additionally, SWRO provides predictable water quality, which helps maintain efficient cooling tower cycles and overall water use effectiveness. One key constraint to note is that the SWRO output is intended specifically for cooling tower makeup water, not for the IT secondary coolant system. The IT equipment requires a separately managed, high-quality closed-loop fluid designed to meet its strict requirements. Finally, we consider the coastal intake and outfall design carefully, as both the SWRO process and the discharge or reject brine necessitate thorough marine environmental reviews. The entire water and cooling infrastructure is designed as part of coastal utility campus, ensuring back-of-house systems are robust, efficient, and suited to the unique coastal conditions of Batam and Nong Sa. Let's talk about the site utility logic for this coastal island data center water supply project. First, it's important to understand that the water plant here must function like critical infrastructure. It's not just a simple process skid. This means it has to be reliable, robust, and fully integrated into the overall utility system. Starting with site context, there are marine and civil constraints we have to address. For example, the intake and outfall need to be separated to avoid recirculating brine or concentrate back into the system. Storm surge and coastal flooding are real concerns, so we use corrosion-resistant materials to handle these harsh conditions. Additionally, obtaining marine environmental permits is essential to regulate the discharge of brine and blowdown water from the cooling towers. On the electrical and control side, all key components like the SWRO units, makeup pumps, and critical instrumentation must be powered from essential power distribution to ensure continuous operation. We also designed the plant to be staged based on tank levels and water use efficiency targets, making it adaptable and efficient. Integration with the building management system and data center infrastructure management tools enables detailed reporting and streamlined operations. Reliability is a major focus, so we implement an N+1 redundancy for both the SWRO trains and pumps. We also design dual product tanks or sectionalized storage to provide flexibility and continuous supply. Isolation valves and bypasses are incorporated, allowing maintenance activities without interrupting the makeup water supply. Finally, from an engineering standpoint, it's crucial to keep cooling tower makeup water quality, facility water quality, and IT secondary coolant quality as separate specifications. Mixing these boundaries can pose significant design risks, especially in liquid-cooled data centers. So we take careful measures to manage these different water qualities properly. Overall, this comprehensive approach ensures that the water supply system is resilient, efficient, and tailored to the unique challenges of a coastal island environment. Here, we're looking at the IT load basis, which forms the foundation for all our thermal, pumping, and water calculations. The design is based on a total IT load of 144 megawatts, divided into 6 modules of 24 megawatts each. This modular approach allows flexibility in deployment and management. Of the total 144 megawatts, about 80% or 115.2 megawatts is managed through direct-to-chip liquid cooling. This means a majority of the heat generated by servers and storage is captured directly at the chip level using cold plates and cooling distribution units, or CDUs. The remaining 20%, approximately 28.8 megawatts, is residual heat that leaves as airside heat in areas like the data hall, maintenance and monitoring rooms, and electrical rooms. Even with direct liquid cooling in place, this heat still needs to be expelled from the building, typically through cooling towers, chillers, or hybrid heat rejection systems. Understanding this load split is critical because liquid cooling reduces reliance on traditional air cooling solutions, such as CRH units and chillers, shifting the load towards facility water loops connected to the CDUs. This shift influences the overall water demand, which varies depending on total heat rejection and the operating mode of the cooling towers. Finally, while liquid cooling can improve power usage effectiveness, or PUE, it's important to carefully manage water usage effectiveness, or WUE. This is achieved through strategic decisions like selecting appropriate cooling towers and integrating seawater reverse osmosis, or SWRO, to optimize freshwater use. This comprehensive training package, centered around the Batam Coastal Data Center, covers all these aspects, from water supply and desalination to advanced cooling integration. Let's take a closer look at the heat flow in this data center and how the heat travels from the IT equipment all the way to the atmosphere. The total IT load is 144 megawatts, which represents the amount of heat generated by the IT racks. Out of this, about 115 megawatts are carried away through the direct liquid cooling path, which efficiently transfers heat from the IT racks using a secondary coolant loop. The remaining 29 megawatts are removed via the residual air path. This dual-path approach optimizes how heat is managed. The coolant then passes through the CDUs, or cooling distribution units, which act as heat exchangers. It's important to note that CDUs themselves don't remove heat from the site. They simply transfer the heat from the secondary coolant to the facility water loop. From there, the facility water moves through the primary loop to the air cooling coils in the CRH units, and then to the chillers, where the condenser heat is managed. Finally, the heat is expelled to the environment through the cooling towers, which handle a load of about 152 megawatts. This design integrates water supply considerations, including seawater reverse osmosis desalination and a combination of direct liquid cooling with cooling tower systems, specifically tailored for the Batum Coastal Data Center. Understanding this heat flow path is crucial because it directly influences water use, energy needs, and the overall reliability of the facility. This slide provides an overview of the key formulas used throughout the presentation, which form the backbone of our calculations. All of these are based on transparent heat balance and water balance equations, ensuring accuracy and clarity in our analysis. We start with a sensible heat transfer formula, which calculates heat transfer in water using flow rate, heat capacity, and temperature difference. This is crucial for understanding how much heat energy is being moved within the system. The hydronic flow calculation is derived from this, allowing us to determine the volumetric flow rate of water or chilled water in different cooling circuits. Next, we look at the chiller condenser heat equation, which ties together the heat rejected by the chiller condenser, the evaporator, and the compressor power, incorporating the coefficient of performance for realistic efficiency assessments. For cooling towers, evaporation loss is calculated based on the heat load and the latent heat of vaporization, helping us estimate water losses during cooling. Blowdown and make-up water formulas and allow us to quantify water management aspects by calculating how much water is discharged and how much needs to be replenished, emphasizing the importance of minimizing leaks and overflow. Water usage effectiveness, or WUE, is an essential metric that links annual water use to IT energy consumption, highlighting sustainability and efficiency in the data center operation. Finally, the SWRO feed formulas explain feed water and brine calculations during seawater reverse osmosis desalination, accounting for pretreatment losses to give a complete picture of water intake and rejection. Together, this formula library supports the training concepts around the Batum Coastal Data Center's water supply, seawater desalination, direct liquid cooling, and cooling tower integration, providing a solid foundation for water and heat management strategies throughout the deck. Here are the key calculation assumptions for our training and concept development. Keep in mind, these values are preliminary and will need refinement once we select vendors, analyze local weather data, and assess site-specific water chemistry. First, the total IT load is set at 144 megawatts, split across 6 modules of 24 megawatts each. Of this, about 80%, or roughly 115 megawatts, is directly captured at the chip level through cooling distribution units, maximizing direct liquid cooling efficiency. The remaining 20% represents residual heat handled by traditional airside equipment, like computer room air handlers and chillers. We've also assumed specific temperature differentials in various cooling loops, a 10 Kelvin change in the secondary coolant loop between the racks and the cooling distribution units, and an 8 Kelvin differential in both the primary facility water loop and the condenser water for the cooling towers. These values reflect typical operating ranges to optimize heat exchange performance. For the chiller's efficiency, we're using a coefficient of performance of 7.0, which is a concept value typical for water-cooled chillers. The concentration of cycles for the cooling towers is 6, used as a baseline for comparing open, closed, and hybrid cooling approaches. This value might be adjusted higher if water chemistry conditions support it. Lastly, seawater reverse osmosis recovery is set at 42%, representing the proportion of seawater converted into usable freshwater in the desalination process, powering the facility's cooling needs. Overall, these assumptions provide a solid framework for the training concept package focused on the Batum Coastal Data Center, combining seawater desalination, direct liquid cooling, and integrated cooling towers. As we move forward, these parameters will be refined to ensure accurate design and optimal performance. Now we're diving into Section 2, which focuses on liquid cooling, CDU selection, and facility water sizing. Here, we'll explore how direct-to-chip heat capture works and why choosing the right cooling distribution unit, or CDU, is critical for efficient thermal management. We'll also cover the role of rack secondary coolant systems and how they influence facility water flow and pump requirements. This training module uses a Batum Coastal Data Center as a case study, integrating real-world elements like seawater reverse osmosis desalination, direct liquid cooling technologies, and cooling tower systems. Understanding these components and their interactions will give you a comprehensive view of how to design and size cooling infrastructure effectively for high-performance data centers. Here, we're focusing on the CDU reference, specifically a high-capacity 2.3 megawatt class unit. This capacity was chosen because it corresponds to a commercially available liquid-to-liquid CDU class, which means we're not tied to any particular brand or proprietary design. This makes the sizing more flexible and practical for a wide range of applications. The training concept package ties together multiple components. It includes a Batum Coastal Data Center's water supply, seawater reverse osmosis desalination, direct liquid cooling, and integration with the cooling tower. All these elements come together to create an optimized cooling strategy. The CDU itself is a liquid-to-liquid heat exchanger, which effectively separates the facility water from the secondary coolant that circulates through the IT equipment. The nominal capacity is 2.3 megawatts per unit, making it large enough to reduce the total number of units needed in multi-megawatt AI or high-performance computing pods, yet still compact enough to be distributed modularly or to mechanical galleries. The benefits of the CDU class extend beyond just size. It supports high-density, direct-to-chip cooling clusters and allows for centralized monitoring, offering both efficiency and ease of management. However, it's important to note that this capacity class is a starting point. The detailed design, including the specific CDU model, type of heat exchanger, pump head requirements, materials, filtration systems, and secondary fluid chemistry, must be finalized in close consultation with the IT original equipment manufacturer and the CDU supplier to ensure compatibility and optimal performance. Here we're looking at the sizing and selection criteria for the cooling distribution units, or CDUs, which are critical for managing the thermal load at our Batum Coastal Data Center. The selection is organized for a 24 megawatt module, which allows us to deploy the infrastructure in phases and makes maintenance more manageable over time. The key parameters start with a direct liquid load per module, calculated as 80% of the 24 megawatt module capacity, resulting in 19.2 megawatts. For the CDU capacity, we're using commercial units rated at about 2.3 megawatts each. To meet the 19.2 megawatt load, we need 9 CDU units operating per module. However, to ensure reliability and maintainability, we install one additional standby unit per module, bringing the total to 10 units installed per module. Since there are 6 modules on campus, this totals 60 installed CDU units. In terms of capacity, the total duty capacity across 54 units is 124.2 megawatts, while the full installed capacity, including the standby units, sums up to 138 megawatts. An important check is a concurrent maintainability. Even if one CDU is taken offline per module for maintenance, the remaining capacity of 20.7 megawatts exceeds the required 19.2 megawatts, ensuring continuous operation without thermal performance compromise. This approach, combined with the training concept package covering water supply, desalination, direct liquid cooling, and cooling tower integration, ensures a robust and maintainable cooling infrastructure for the data center. Here we have the CDU module topology based on a 24 megawatt IT module. This modular approach offers several advantages, particularly in simplifying isolation and commissioning processes, as well as supporting Tier 3 or Rated 3 demonstration requirements. The The training concept package focuses on integrating multiple advanced systems at the Batum Coastal Data Center, including its water supply, seawater reverse osmosis desalination, direct liquid cooling, and cooling tower operations. Each module, such as Module 1, 2, and 3, is designed around 24 megawatts of IT capacity with 19.2 megawatts dedicated to direct liquid cooling. Within each module, there are 10 CDU units installed, each rated at 2.3 megawatts. Importantly, out of these 10 CDUs, 9 act as duty units providing a combined capacity of 20.7 megawatts, which exceeds a direct liquid cooling design load of 19.2 megawatts. This configuration ensures there is always reserve capacity. That means one CDU can be taken offline for planned maintenance at any time without impacting the overall cooling support for the module. This modular and redundant setup not only increases operational flexibility, but also enhances system reliability, enabling continuous cooling performance critical for high-density data center operations. Here we have an overview of the TCS secondary flow, which refers to the secondary coolant loop running from the CDU to the server and storage cold plates. It's important to note that this loop is part of the clean IT side cooling system. Unlike other cooling loops, it does not use water from a cooling tower or SWRO desalinated water. This distinction is critical for maintaining system cleanliness and performance. Looking at the technical side, this loop handles about 115.2 megawatts of direct liquid heat in the campus, which is calculated as 80% of the total 144 megawatts. The temperature difference in the secondary loop is around 10 Kelvin, with supply and return temperatures at approximately 32 and 42 degrees Celsius, respectively. Using this temperature difference in heat load, we calculate the required cooling water volume flow. For example, the overall campus TCS secondary flow comes out to roughly 9,907 cubic meters per hour. Breaking it down further, a 24 megawatt module needs about 1,651 cubic meters per hour, while a single 2.3 megawatt CDU requires about 198 cubic meters per hour. These calculations ensure the system maintains optimal cooling capacity. Visually, the rack secondary coolant loop channels this fluid directly to the cold plates, providing efficient heat transfer. When it comes to fluid selection, the loop uses OEM-approved treated water or a propylene glycol mixture if freeze protection is necessary. At the Batum site, freeze protection is generally not required. Additionally, the fluid needs to have corrosion inhibitors, biocide strategies, filtration to remove particulates, degassing, conductivity monitoring, and leak detection. These measures are essential to preserve the integrity and reliability of the cooling system. Notably, dielectric fluids are generally not needed for these direct-to-chip cold plate loops. They are more relevant for immersion cooling setups. This comprehensive approach ensures efficient and safe operation of the secondary cooling loop in the data center. On this slide, we're focusing on the coordination between the rack's secondary fluid loop and the power distribution units, or PDUs, within a data center environment. Even though the liquid cooling loop and the electrical power systems are fundamentally separate, it's critical to manage them together at the rack row level to ensure reliability and efficiency. The secondary coolant loop is a closed, high-quality system that runs from the cooling distribution unit, or CDU, to the rack manifolds and cold plates. This loop must maintain strict particle filtration and stable chemical balance to prevent contamination, and it's essential to avoid oxygen ingress, which can degrade the system over time. Leak detection is another key requirement, with sensors placed at the CDU, manifold, and under the rack in strategic drip detection zones to catch any issues early. When it comes to the power distribution units, they must be physically separated from the liquid manifolds to reduce risk and simplify maintenance. Using dripless quick disconnects and organized cable and hose routing helps ensure safe, clean service access. Additionally, we have to carefully coordinate heat output from the PDUs, ensure adequate service clearance, and properly locate sensors and containment systems. It's important to note that the secondary cooling loop typically uses either treated water or a glycol mixture depending on the specifications of the IT equipment manufacturer. Importantly, cooling tower make up water, Seawater reverse osmosis permeate, or raw tower water, should never be connected directly to the IT racks to protect sensitive equipment. This integrated approach is especially relevant in high-density server and storage rack rows, where efficient cooling and power delivery must be managed flawlessly to support demanding operational needs. The setup here, illustrated by the BATM Coastal Data Center case, includes water supply, SWRO desalination, direct liquid cooling, and cooling tower integration as part of a comprehensive training concept package. Here we're focusing on the facility water flow, specifically the primary water loop that connects the CDU or cooling distribution unit to the heat rejection plant. The primary side of the CDU plays a crucial role by transferring heat from the CDU to the facility's heat rejection system, helping manage the thermal load effectively. This training concept package covers several integrated systems, including the BATM Coastal Data Center water supply, seawater reverse osmosis desalination, direct liquid cooling, and the cooling tower integration, all working together to optimize cooling efficiency. Looking at the calculations, the direct liquid heat captured at the chip level is 115.2 megawatts. To account for losses and allowances for the CDU, pump, and heat exchanger, a 3% increase is added, bringing the design heat on the facility loop to about 118.7 megawatts. The temperature difference for facility water is set at 8 Kelvin, which could represent a typical operating range like 36 to 44 degrees Celsius, or adjusted to project-specific conditions. Using the hydronic flow formula, the campus-level CDU primary flow calculates to approximately 12,756 cubic meters per hour, which when divided by 6 modules results in per module flow of about 2,126 cubic meters per hour. On the pump design side, the facility water pump system can be modularized around a 24 megawatt capacity per module. For example, each module might be served by 4 duty pumps plus 1 standby variable frequency drive pump, each with a flow capacity of around 550 cubic meters per hour. Final pump selection will depend on detailed hydraulic head calculations, ensuring the system is optimized for efficiency and reliability. Let's dive into the logic behind selecting the facility's water pumps. The key here is to ensure the pump quantity supports maintainability, allows for low load turndown, and maintains stable CDU differential pressure throughout operations. This balance is crucial for reliable and efficient cooling performance. Our training concept package covers the BATM Coastal Data Center's water supply, integrating SWRO desalination, direct liquid cooling, and cooling towers. When we look at the pumps themselves, the primary or condenser pump skid includes VFD pumps equipped with isolation valves and bypass lines, allowing for flexible control and maintenance. From the table, you can see the core design parameters. Each module requires about 2,126 cubic meters per hour of direct CDU primary flow, based on a 19.2 megawatts module plus a 3% margin. To achieve this, we plan an arrangement of 4 duty pumps plus 1 standby per module, ensuring concurrent maintainability. Each pump handles roughly 650 cubic meters per hour, collectively exceeding the module's required flow to provide a safety buffer. Across the campus, this means 30 pumps in total, 5 pumps per module for 6 modules. We control these pumps using a variable frequency drive based on differential pressure, which keeps the CDU's primary differential pressure stable over the whole operating range. However, we still need to finalize these specifications using a detailed hydraulic model that captures pressure losses through headers, valves, heat exchangers, and cooling towers. A critical note on redundancy: to meet Tier or rated 3 readiness, any component, whether it's a pump, VFD, isolation valve, or strainer within a maintainable segment, must be removable without losing the critical cooling function. This ensures continuous operation even during maintenance or unexpected failures. Here, we're focusing on residual air cooling, which deals with the portion of heat that isn't captured by direct liquid cooling. Specifically, about 20% of the IT load generates residual airside heat that must be managed via airside cooling systems. This residual heat, calculated at 28.8 megawatts, comes from various sources such as memory, storage, network equipment, power supplies, leakage heat, and even the room envelope itself, including maintenance and operational areas. In high-density AI data halls, these airside systems play a crucial role. The equipment used for this purpose can vary, including CRH units, fan walls, in-row cooling, or rear door heat exchangers. The choice depends heavily on the rack layout and the specific cooling needs of the space. Regarding chilled water flow, we use a delta T of 8 Kelvin within the chilled water loop. The calculation for chilled water flow volume is based on the heat load and temperature difference, following the formula V equals Q times 0.86 divided by delta T for this campus setup. That results in approximately 3,096 cubic meters per hour split across 6 modules, each handling around 516 cubic meters per hour. Overall, this integrated approach leverages seawater reverse osmosis desalination, direct liquid cooling, and cooling tower systems, ensuring efficient management of residual heat through carefully designed airside cooling components. Here, we focus on the CRH and FW selection process for managing the residual heat load of 28.8 megawatts. The number of units required depends on several factors: the capacity of each unit, how the data hall is divided into zones, the type of containment used, and the overall redundancy strategy. In our training concept package, we've incorporated systems such as BATM Coastal Data Center Water Supply, SWRO desalination, direct liquid cooling, and cooling tower integration to optimize this process. On the air side, the calculation for residual load per module is 4.8 megawatts, which is simply the total 28.8 divided across 6 modules. For the high-flow chilled water units, we assume capacity of 200 kilowatts each. This means each module requires 24 duty units. That's 4.8 megawatts divided by 0.2 megawatts per unit. To ensure reliability, we add redundancy at the room or module level, following an N+2 approach. So, for each module, 24 units are active and 2 are on standby, bringing the total to 26 units per module across the entire campus. That sums up to 156 units. The final selection process involves detailed vendor data, including airflow and coil performance. It's critical to verify external static pressure and supply temperature to ensure system compatibility and efficiency. Finally, control of the airside units is essential. CRH and FW controls need to work in harmony with the liquid cooling systems, monitoring rack inlet temperatures, differential pressures, containment effectiveness, and integrating feedback from building management systems and DCIM thermal analytics to maintain optimal environmental conditions. Let's talk about chiller selection for the residual airside load in our data center cooling system. We're focusing on water-cooled chillers designed specifically to handle the airside residual load and support spaces, rather than the direct liquid load managed by the CDU units. Based on the data, the evaporator load is 28.8 megawatts, which reflects the residual airside cooling demand. We assume a coefficient of performance, or COP, of 7.0 as a conceptual value. This means for every unit of power we put into compressor, we get 7 units of cooling output. Using this, the compressor heat input is calculated at 4.1 megawatts, while the total condenser heat, comprising both evaporator and compressor heat, is about 32.9 megawatts. For system arrangement, there are 2 options: one central plant with 7 chillers rated at 5 megawatts each, where 6 run in duty and 1 is on standby, or a modular setup with 3 modules each having 3 chillers at 2.4 megawatts, maintaining 2 duty and 1 standby per module. A critical aspect here is redundancy. For a Tier 3 or rated Tier 3 design, every component, including chillers, condenser, and chilled water pumps, tower cells, and control systems, must be configured so that planned maintenance on any one part doesn't disrupt the overall critical IT cooling function. On the right, we have a vendor-neutral, top-view illustration of a smart-style oil-free water-cooled chiller. This diagram highlights key components: compressors or motor pods where oil-free compressor sections are located, the evaporator barrel absorbing chilled water heat, and the condenser barrel rejecting heat to tower water. The control cabinet manages unit operation and power, while the chilled water supply and return lines handle cooling delivery and warmer water coming back from the load. Finally, condenser water supply and return lines connect back to the cooling tower and the refrigerant expansion and control device regulate the refrigerant flow. This comprehensive approach ensures efficient, reliable, and maintainable cooling tailored to unique demands of our coastal data center environment. Here we see the condenser water flow for the residual airside chiller plant. The condenser heat generated here is combined with the direct liquid heat at the cooling tower or hybrid cooler, which makes the overall cooling process more efficient. Looking at the table, the airside chiller evaporator load is 28.8 megawatts, which represents the residual air heat being removed. The compressor contributes an additional 4.1 megawatts of heat based on the ratio of evaporator load to the coefficient of performance, or COP. Adding these together gives us the total condenser heat rejection of 32.9 megawatts. The condenser water temperature rises by 8 Kelvin across the cooling tower, which is our delta T or temperature difference. Using the formula shown, where water flow volume equals the heat load multiplied by 0.86 divided by delta T, we calculate the condenser water flow rate to be about 3,538 cubic meters per hour. This flow is then divided by 6 modules on the campus, resulting in around 590 cubic meters per hour per module. This breakdown helps to optimize the water flow requirements for maintaining efficient cooling tower and chiller operation within the BADM Coastal Data Center's integrated system. Here, we're looking at the heat rejection summary for the cooling system. The key point is that when selecting cooling towers, we need to account for both the direct liquid heat load from the IT equipment and the heat from the water-cooled chiller condenser. The direct liquid cooling system captures about 115.2 megawatts, which is 80% of the IT load. We then add a small allowance of 3% for facility loop, bringing that number to 118.7 megawatts directed towards heat rejection. The chiller condenser adds another 32.9 megawatts, which combines heat from the evaporator and compressor. When you total these together, the system must reject about 151.6 megawatts of heat. The cooling towers are designed to handle this combined load, not just a direct liquid cooling loop. The water temperature change, or delta T, across the condenser is set at 8 Kelvin, which impacts the water flow rate needed for the towers. This results in a total tower water flow of approximately 16,297 cubic meters per hour. In summary, the design ensures that the cooling towers accommodate all heat sources in the facility, guaranteeing reliable and efficient heat rejection from both the direct liquid cooling and the chiller condenser systems. Now, let's dive into Section 3, where we'll explore various cooling tower alternatives and the associated water balance considerations. We'll cover the calculations for different types of cooling towers, open wet, closed wet, and hybrid closed adiabatic systems, and compare their corrected water usage. This is crucial for understanding how each technology impacts overall water consumption. Our training concept package focuses on the BADM Coastal Data Center, incorporating local water supply specifics, seawater reverse osmosis desalination, direct liquid cooling methods, and how these systems integrate with cooling towers. By the end of this section, you'll have a solid grasp of how to optimize cooling tower selection and water management for efficient, sustainable data center operations. Here, we're focusing on the cooling tower water balance and the method used to calculate makeup water requirements. The key principle is a fundamental mass balance, which applies uniformly across open, closed, and hybrid cooling tower systems. Let's break down the main components listed in the table. First, evaporation represents the dominant water loss in the cooling tower process. It's calculated based on a heat load in kilowatts, converted to the latent heat of vaporization, with HFG approximately 2,440 kilojoules per kilogram. This loss is significant because it directly reduces water volume in the system. Next is blowdown, which is water intentionally discharged to prevent the buildup of impurities. It's determined by dividing the evaporation rate by the cycles of concentration -1. Managing blowdown is crucial because it keeps the water chemistry in check by controlling total dissolved solids. Drift refers to small droplets of water carried out with the exhaust air. Although usually minimal compared to evaporation and blowdown, it still needs to be considered in the overall water balance. Makeup water is the total amount needed to replace all losses, evaporation, blowdown, and drift, to maintain the system's water level. Cycles of concentration, or COC, express the ratio of total dissolved solids in the tower water to those in the makeup water. Increasing the COC reduces the blowdown rate, but requires careful water chemistry control to avoid scaling or corrosion. Lastly, the hybrid wet fraction accounts for partial dry or adiabatic operation in hybrid cooling towers. This is modeled by multiplying the wet evaporation rate by the fraction of time the wet mode is active. Understanding these terms and how they connect helps in designing and maintaining efficient cooling tower systems, particularly in complex setups like our Badham Coastal Data Center, where integration with desalination and liquid cooling technologies is critical. Let's take a closer look at the open circuit wet cooling tower, which plays a key role in the Badham Coastal Data Center's cooling system integration. The operating principle here is straightforward. The condenser or facility water is exposed directly to the air. This direct contact is what cools the water as it falls over the fill material, maximizing air-water interaction. This design offers the advantage of a low approach temperature and simpler hydraulics, which often translates to lower equipment complexity and upfront costs. However, because the circulating water is open to ambient air, it is more susceptible to fouling from dust, biological contaminants, and drift. This means that chemical treatment and side stream filtration become critical to maintaining system performance. From a design standpoint, there are several important components to note. Axial fans induce airflow, while drift eliminators minimize water loss by reducing carryover. Water is distributed evenly over the fill pack to maximize cooling efficiency, and air inlets draw outside air into the tower. Cooled water collects in the cold water basin before returning to condenser. Key flows include the hot water entering the tower, cooled water exiting, the air path to the system, blowdown or bleed off to control impurities, and makeup water to compensate for losses. The main takeaway from this training is that the type of cooling tower directly influences water exposure, treatment needs, control strategies, physical footprint, and water use efficiency. It's essential to base water-saving estimates on actual evaporation, blowdown, drift, and wet fraction calculations rather than assumptions tied to tower types or names. This ensures proper system design and operational efficiency in the data center cooling process. Here, we walk through the open cooling tower calculation using the water balance method, where the makeup water required equals the sum of evaporation, blowdown, and drift losses. Starting with heat rejected to the tower, we combine the facility heat load and the chiller condenser load to get 151.6 megawatts. From this, evaporation loss is calculated using the latent heat of vaporization, resulting in 223.7 cubic meters per hour or 5,368 cubic meters per day. Next, we estimate the recirculation flow used to determine drift losses, arriving at around 16,297 cubic meters per hour. Blowdown is then calculated considering a cycles of concentration of 6, giving us about 44.7 cubic meters per hour. Drift loss, although much smaller, is computed as 0.001% of the recirculation flow, which equates to roughly 0.163 cubic meters per hour. Adding these components together, the total makeup water requirement comes to approximately 268.6 cubic meters per hour, or 6,446 cubic meters per day. To ensure reliability, a seawater reverse osmosis system with a 10% margin is sized at about 7,091 cubic meters per day. From an engineering perspective, open wet cooling towers offer straightforward hydraulics, but the water in the facility loop is exposed to the atmosphere, making evaporation the dominant water loss. Blowdown also plays a significant role and must be accurately validated based on selected cycles of concentration. This comprehensive calculation equips us with a solid understanding of water needs for the cooling tower in this coastal data center environment. Here we have an open circuit flow diagram that illustrates the key processes involved in the seawater reverse osmosis, or SWRO, system for the Badham Coastal Data Center's water supply. The diagram clearly separates the makeup water entering the system from the evaporation and reject streams, which are crucial components in managing water balance. Starting with the SWRO product tank, it provides low TDS or low total dissolved solids, makeup water to the system. This water is then pumped by the makeup pumps, which are equipped with variable frequency drives and meters to carefully control flow rates. The open cooling tower is where heat rejection takes place through evaporation, releasing water vapor into the atmosphere. In this process, about 223.7 cubic meters per hour of water is evaporated. Additionally, blowdown of 44.7 cubic meters per hour occurs to prevent salt buildup, and this reject stream undergoes neutralization and monitoring before disposal as waste or outfall. The open tower's water demand is the sum of evaporation, blowdown, and a small amount for drift loss, totaling approximately 268.6 cubic meters per hour, or just over 6,400 cubic meters per day. This figure represents the baseline wet tower water consumption for the system, which is a critical parameter for operational planning and environmental management. Here we have the closed-circuit cooling tower, an important component in the integration of BATM's coastal data center water supply, including seawater reverse osmosis desalination and direct liquid cooling. The key operating principle here is that the facility's process fluid remains inside a closed heat exchanger coil, separated from the spray water that is sprayed over the coil and evaporates outside it. This separation means the process fluid loop is closed and stays much cleaner than an open cooling tower system. From a design perspective, this closed loop offers significant advantages. The process fluid is protected, reducing contamination risks, while the spray loop still requires chemical treatment and blowdown to manage water quality. Water consumption is roughly similar to an open wet cooling tower when performing the same heat rejection. These towers are preferred when protecting heat exchangers and cooling distribution units is critical. The training takeaway here is to understand that the cooling tower type directly affects water exposure, the required treatment, operational controls, footprint, and water use efficiency. It's important not to assume water savings just based on equipment labels, but to calculate them using detailed factors like evaporation, blowdown, drift, and wet fraction formulas. Looking at the components, axial fans create the induced draft to move air through the tower, while drift eliminators reduce water carryover. Spray headers distribute water uniformly, and the closed heat exchanger coil keeps the process fluid contained. A recirculation pump returns water from the cold water basin back to the spray headers. Key flow paths include hot process fluid entering, cool fluid exiting, spray water circulating, blowdown for water discharge, and warm air being exhausted. Overall, the closed-circuit cooling tower offers a controlled, efficient approach to heat rejection with clear benefits for sensitive data center cooling applications. Let's go through the calculations for the closed-circuit cooling tower, focusing on makeup water requirements. First, we note that for the same heat rejection duty, the closed wet tower's evaporation loss is essentially the same as an open wet tower. This is because the coil protects a facility loop but doesn't increase the latent heat load. Starting with heat rejection, the closed tower rejects 151.6 megawatts, identical to the open system. Using this, we calculate evaporation loss, which comes out to 223.7 cubic meters per hour, or about 5,368 cubic meters per day. Next, considering recirculation or spray equivalent flow for drift, we get a value of around 16,297 cubic meters per hour. The blowdown rate at a cycles of concentration of 6 is 44.7 cubic meters per hour, ensuring that water quality is maintained. Drift loss is minimal, just 0.081 cubic meters per hour, or around 2 cubic meters a day, which is only 0.0005% of the recirculation flow. Adding these components together, the total makeup water needed is 268.5 cubic meters per hour, or roughly 6,444 cubic meters per day. Comparing this to an open tower, the difference is negligible, about 2 cubic meters per day, or just 0.03% less water use. The water use efficiency, or WUE, is 1.86 cubic meters per megawatt hour. From an engineering perspective, closed wet towers are valuable because they protect the facility's water loop from airborne contamination. However, their evaporation remains driven by heat rejection, just like open towers. So, the closed wet tower should be considered primarily as a strategy for loop protection and maintaining water quality, rather than a strong water-saving measure, unless paired with equipment or chemistry that allows higher cycles of concentration or hybrid dry/adiabatic operations. Here we have the closed circulating water flow system, which is designed to keep the facility loop completely closed, meaning the water inside the process or facility doesn't leave this loop. This is important because it minimizes water loss and contamination inside the cooling loops. At the same time, there's a separate spray loop that's open to the atmosphere. This spray circuit is where water evaporates, and as a result, this loop consumes makeup water to replace what's lost through evaporation. The integration of components like the SWRO desalination system and direct liquid cooling in this setup ensures efficient water supply and cooling for Batum Coastal Data Center. Specifically, the closed-circuit chiller loop circulates water within the facility without any direct air contact, protecting the quality of the water and maintaining cooling efficiency. Heat rejection happens in the closed cooler coil via fans and sprays, where evaporation to the atmosphere takes place in the spray basin. Makeup water flows into the system from the SWRO product tank to compensate for what evaporates, while the spray basin level and conductivity are carefully monitored. Blowdown or wastewater discharge comes specifically from the open spray basin and not from the closed loop, regulated through conductivity set points and valves. The key point here is understanding that the closed circuit protects the internal cooling loop and water quality, but does not eliminate the need for tower makeup water because of evaporation losses in the open spray basin. This distinction is fundamental for water conservation and system performance. This slide presents the hybrid closed adiabatic cooling tower concept, which is especially valuable for data centers with specific cooling and water efficiency needs. The key idea here is that hybrid units primarily use dry coils to reject heat when conditions allow. This means the system operates in dry mode with fans and closed coils, which significantly reduces water use. However, when ambient temperatures and loads increase beyond a point where dry cooling alone is sufficient, the system shifts to a wet assist mode. In this mode, adiabatic pre-cooling sprays water on media pads to cool the incoming air, enabling increased heat rejection. This staged approach ensures water is only used when absolutely necessary, making it a true water-saving option by reducing wet operating hours. Designing these systems brings some important implications. They require sophisticated control logic that monitors ambient wet bulb and dry bulb temperatures to decide when to switch between dry and wet modes. Because of the added components like spray headers, recirculation pumps, and makeup water valves, the footprint is larger and controls are more complex. Also, an all-wet contingency or backup water strategy must be included for periods requiring continuous wet operation. From a training perspective, understanding this tower type is critical because it affects water exposure and treatment needs, control strategies, and overall water use efficiency. We can't just assume water savings based on the name. Instead, we need to calculate evaporation, blowdown, drift, and wet fraction formulas to prove actual water efficiency. Looking at the schematic components, the axial fan induces airflow, while the dry heat exchanger coil handles closed fluid cooling. The air inlet louvers allow outside air intake, and the adiabatic media pads pre-cool the air when sprayed by the distribution header. The wet assist water loop includes a recirculation pump, makeup water valve, and bleed valve to manage water cycles and prevent wastewater buildup. The hot process fluid enters from facility heat load, and once cooled, it is returned to facility loop with warm air discharged to the atmosphere. Finally, all these processes are managed by integrated controls and sensors that monitor fan operation, pump activity, ambient conditions, and water quality to optimize performance and ensure efficient, reliable heat rejection with minimal water use. Here we dive into the concept of hybrid cooling towers, or hybrid CT, with a focus on calculating water use based on the wet operating fraction. Essentially, the hybrid operation water calculation starts with the baseline water usage of an all-wet closed-circuit system and adjusts that according to the expected fraction of time the system operates in wet mode. We have three key wet mode scenarios here. The optimized case assumes a 45% wet fraction, representing a more efficient, favorable operational scenario. Then there's a conservative case at 65%, which is used for humid coastal environments like the Batum Coastal Data Center, example we're training on. Finally, The all-wet scenario assumes 100% wet operation as a contingency plan, reflecting the highest water use of dry or adiabatic modes can't maintain target temperatures. To give perspective, the baseline all-wet closed-circuit makeup water use is about 6,444 cubic meters per day. The wet equivalent heat rejection, which is the heat our cooling system needs to handle, is 151.6 megawatts, based on the same campus heat rejection. The critical formula guiding this is M hybrid equals M wet times F wet, meaning the hybrid water use equals the baseline wet water use multiplied by the fraction of wet operation. This formula is applied across evaporation, blowdown, and drift losses within the system. Ultimately, selecting the final hybrid cooling strategy requires detailed hourly simulation using local climate data, like Badham's dry bulb and wet bulb temperature distributions, water supply temperature targets, cooling tower fan power, and validated wet mode hours. This approach ensures a cooling design is both effective and water efficient under specific site conditions. Here we are looking at the hybrid closed adiabatic cooling tower calculation, focusing on detailed makeup water scenarios. The key advantage of hybrid operation is that it reduces annual water use by operating dry or in adiabatic mode for part of the time. Only when the system runs in wet mode do we consume evaporation and blow down water. This slide outlines a training concept package built around Badham's coastal data center water supply, integrating SWRO desalination, direct liquid cooling, and the cooling tower system. We see three scenarios comparing different wet fractions: optimized hybrid at 45%, conservative hybrid at 65%, and an all-wet contingency at 100%. The equations show how makeup water volume is adjusted by multiplying closed-circuit makeup by the wet fraction to find the daily water requirement. The step-by-step formula begins with the all-wet closed-circuit makeup value, then selects a wet fraction based on climate and controls. Evaporation, blowdown, and drift are all scaled by this wet fraction, and the total makeup water is the sum of these components. Finally, from a control perspective, hybrid water usage depends directly on wet mode hours. Monitoring the wet fraction along with entering wet bulb temperature, facility water exit temperature, and makeup water meters in the building management or data center infrastructure management systems is essential. For design and risk management, the system must account for full water demand in an all-wet contingency scenario or have equivalent backup water supply strategies in place. Here we compare different cooling tower alternatives based on their water use efficiency at a consistent heat rejection duty of 151.6 megawatts. You'll see that open circuit wet and closed circuit wet systems have almost identical daily water makeup demands, around 6,444 to 6,446 cubic meters, resulting in virtually the same water use efficiency, or WUE, of approximately 1.86 to 1.87 cubic meters per megawatt hour. Closed wet systems do offer the advantage of a cleaner facility loop, which helps protect equipment, but they don't significantly reduce water consumption compared to open wet systems. The real water savings come from hybrid closed adiabatic systems. When optimized, these systems cut the daily makeup water demand down to about 2,900 cubic meters, with much improved WUE of 0.84. Even under more conservative operating conditions, hybrid systems still outperform traditional wet towers, using roughly 4,188 cubic meters daily and achieving a WUE of 1.21. This shows how important incorporating dry or adiabatic operation modes is for reducing water use. However, if dry or adiabatic modes are unavailable and the system operates fully wet on contingency, water use jumps back up to levels similar to traditional wet cooling towers. To summarize the key takeaway, while closed wet towers protect the system loop, they don't drastically change water consumption. The meaningful reductions are achieved through hybrid dry/adiabatic cooling, carefully controlled wet operation, regular WUE measurement, and having a water security contingency plan ready. This integrated approach is essential for sustainable water management in high-demand cooling applications like the Badham Coastal Data Center. When selecting between open, closed, and hybrid cooling towers, several important factors need to be considered. These include water usage, energy consumption, system reliability, risk of contamination, and whether the solution meets specific certification targets. Looking at the key criteria, Open wet towers generally have the lowest initial cost, but come with higher water consumption and lower facility loop cleanliness. They also have moderate maintenance complexity and lower fan energy use. Closed wet towers offer better loop cleanliness and are good for Tier 3 ratings, though their first cost and maintenance needs are slightly higher. Hybrid closed adiabatic towers have the highest upfront cost and maintenance complexity, but they excel in minimizing water consumption during dry or adiabatic periods, provide excellent loop cleanliness, and have strong potential to support green certification like the Green Mark. However, energy use can be higher due to increased fan energy in dry mode, and controls are more complex. This comparison is essential when planning coastal data centers, such as in Batum, where integration with seawater reverse osmosis desalination and direct liquid cooling systems must be carefully balanced for optimal performance and sustainability. Now we'll focus on the SWRO makeup water plan and distribution, which is a critical part of our water supply system for the Batum Coastal Data Center. Here, we'll dive into several key aspects. First, we'll look at how we size the seawater reverse osmosis desalination system to meet the facility's needs. Then, we'll define the process boundaries, which means understanding where the desalination process starts and ends in the overall water system. We'll also cover how the purified product water is stored after treatment and discuss strategies for managing the brine and blowdown byproducts to minimize environmental impact. Finally, we'll examine the distribution system that delivers this treated water as makeup water throughout the facility. This integrated approach ensures a reliable and sustainable water supply, critical for supporting direct liquid cooling and cooling tower operations at the data center. Here we're looking at the SWRO makeup water plant and its overall process. This plant is designed specifically to produce low TDS makeup water for the cooling tower supply, which is crucial for maintaining efficient cooling operations. It's important to note that this plant is not responsible for preparing the direct-to-chip secondary coolant system. Starting from the seawater intake, raw seawater is first drawn in. Then it goes through pre-treatment stages that include screening, ultrafiltration, and multimedia filtration to remove particulates and prepare the water for desalination. After pre-treatment, chemical dosing is applied. This includes adjusting pH and adding sodium metabisulfite and antiscolants to prevent membrane fouling and scaling. The heart of the system is the reverse osmosis membranes, which perform the desalination process, removing salts and impurities to produce low TDS water. Post-treatment is then applied to stabilize the water's pH, ensuring it's not too aggressive or corrosive for the cooling tower system. The treated water is stored in a makeup tank and supplied to the cooling tower. The goal here is to reduce scaling and support higher cycles of concentration, which improves efficiency. Although the water is stabilized, the cooling tower itself requires its own chemical management program for corrosion control, scale inhibition, microbial control, and blowdown based on conductivity. A key point to remember is the boundary of the system. The SWRO plant supplies only the cooling tower makeup water. The direct-to-chip secondary coolant must be prepared separately as a high-purity, closed-loop fluid following the specifications of the liquid cooling equipment manufacturer. It should never be taken directly from the cooling tower makeup line. This separation is critical to ensure the performance and reliability of the entire cooling system. Let's go through the step-by-step method for sizing an SWRO system, which is based on the cooling tower makeup demand, along with some margin and recovery assumptions. First, we start with the cooling tower makeup water demand, labeled MCT, which we obtain from the tower's water balance. This is the baseline amount of water required to compensate for losses in the cooling tower. Next, we calculate the SWRO net product design, PNET, by multiplying the cooling tower makeup demand by a design margin, in this case 10%. This margin accounts for uncertainties and ensures we have a reliable water supply. Then, to determine the RO feed flow, FRO, we divide the net product by the recovery rate, which is assumed to be 42%. This shows how much seawater feed is needed to produce the net freshwater output. After that, we calculate the brine or concentrate, which is the difference between the feed flow and the net product. This concentrate must be handled carefully, typically sent to a controlled outfall system to comply with environmental regulations. Seawater abstraction comes next. To account for pretreatment losses, we increase the feed flow by 6%, which is the assumed pretreatment loss, giving us a total seawater volume that must be drawn from the source. Then, we determine the number of treatment trains needed by dividing the net product by the capacity of each train, which is 1,500 cubic meters per day net, and rounding up using the ceiling function. For reliability, we install one standby train in addition to the duty trains, following the N+1 maintainability principle. This ensures continuous operation, even if one train is offline for maintenance. Finally, we size the storage to cover between 12 and 24 hours of makeup demand, choosing the exact amount based on the facility's resilience philosophy to ensure continuous supply during any operational interruptions. This approach ensures a well-planned, reliable SWRO system integrated with the cooling tower and overall water supply strategy for the Batum Coastal Data Center. Here, we're looking at the sizing for the seawater reverse osmosis system in an open wet cooling tower scenario. This setup represents the largest practical makeup water demand typically seen with wet towers. Started with a cooling tower, it requires about 6,446 cubic meters per day to make up for water losses. To ensure a safety margin, we increase this volume by 10%, giving us a net product water supply of just over 7,000 cubic meters daily. Next, when feeding the reverse osmosis membranes, we need around 16,884 cubic meters per day, considering a recovery rate of 42%. This means after processing, we expect about 9,793 cubic meters per day of brine or concentrate as a byproduct. To account for abstraction losses, the total seawater intake is slightly higher at nearly 17,900 cubic meters per day. The system is designed with 6 trains of treatment capacity, 5 actively running, each capable of producing 1,500 cubic meters per day, and 1 held in standby for reliability. Finally, to maintain operational stability and provide emergency resilience, the system includes storage buffers equivalent to 12 and 24 hours production, holding 3,223 and 6,446 cubic meters, respectively. This comprehensive sizing ensures continuous, reliable water supply for the Batum Coastal Data Center's cooling and desalination needs. Here, we're looking at the SWRO sizing for a closed-circuit wet cooling tower setup. The key takeaway is that the closed wet system is very similar to an open wet system when operating at the same heat duty. The only difference is a slightly lower drift, which doesn't significantly impact the overall makeup water requirements. Focusing on the table, we see that the cooling tower makeup water volume is 6,444 cubic meters per day, which is a baseline for the closed wet tower. To include a safety margin, the net product is increased by 10%, resulting in 7,089 cubic meters per day. The reverse osmosis feed going into the membranes totals 16,879 cubic meters daily, based on the net product divided by a 42% recovery rate. The brine or concentrate, which is the leftover stream, amounts to 9,790 cubic meters per day, calculated by subtracting the net product from the feed volume. Seawater abstraction is slightly higher at 17,892 cubic meters per day to account for any additional losses, using a 6% increase over the feed water. For capacity planning, the system operates with 5 duty trains that each handle 1,500 cubic meters per day, totaling the net product requirement, plus 1 additional train installed as a standby for reliability. Finally, there's storage for operational resilience, 3,222 cubic meters for a 12-hour buffer, and 6,444 cubic meters for a full 24-hour emergency buffer to ensure continuous supply in case of any interruptions. This setup balances efficient water treatment with operational security for the Batum Coastal Data Center project. Here we have the SWRO sizing for a hybrid closed adiabatic conservative approach. This design is notably smaller, provided the owner agrees to a hybrid operating strategy combined with contingency planning. Taking a closer look at the table, the cooling tower makeup water requirement is 4,188 cubic meters per day under this hybrid conservative daily makeup scenario. To ensure a safety margin, The net product output is calculated at 4,608 cubic meters per day, which is 10% higher than the makeup volume. The reverse osmosis feed to membranes is about 10,972 cubic meters per day, derived from dividing the net product by the recovery rate of 42%. This results in a brine or concentrate volume of 6,364 cubic meters per day, which is a difference between the feed water and the net product. Seawater abstraction is slightly higher at 11,631 cubic meters per day, accounting for a 6% increase to cover operational factors. The system will have 4 duty trains, each capable of handling 1,500 cubic meters per day, with a total of 5 trains installed to include 1 standby unit, ensuring reliability. For operational buffering, a 12-hour product storage of 2,094 cubic meters provides a minimum backup, while full 24-hour storage of 4,188 cubic meters offers resilience in case emergencies. Overall, this sizing approach balances efficiency and reliability through careful integration of hybrid strategies and contingency planning, ensuring a robust supply for the BADM Coastal Data Center's water needs. Here we have the SWRO train count and redundancy by different cooling options, each based on a 1,500 cubic meters per day net train capacity, with an N+1 standby configuration to ensure maintainability. This slide summarizes a training concept package for the BADM Coastal Data Center water supply, covering SWRO desalination, direct liquid cooling, and cooling tower integration. Looking at the cooling options for both the open wet and closed wet setups, the SWRO net design capacity is around 7,090 cubic meters per day, with 5 trains operating and 1 standby, totaling 6 installed trains and 9,000 cubic meters per day of installed net capacity. In contrast, the hybrid optimized approach reduces capacity significantly to about 3,190 cubic meters per day, with 3 duty trains plus 1 standby, totaling 4 trains and 6,000 cubic meters per day installed capacity. The hybrid conservative option provides a mid-range solution with 4,608 cubic meters per day net design for duty plus 1 standby train and 5 trains installed, resulting in 7,500 cubic meters per day of capacity. Finally, the hybrid all-wet contingency matches the open and closed wet configurations at just over 7,000 cubic meters per day, with 5 duty plus 1 standby train, 6 trains installed, and 9,000 cubic meters per day capacity. The key design recommendation here is that if the project opts for a hybrid cooling approach to improve water use efficiency, it's critical to carefully decide whether to size the SWRO for an optimized hybrid, conservative hybrid, or all-wet contingency scenario. This decision goes beyond process calculations, as it involves resilience considerations and commercial factors to ensure the best fit for the project's goals and risks. When it comes to tank sizing for our BADM Coastal Data Center water supply, we focus on storing raw seawater, treated makeup water, and ensuring emergency resilience. The way we size these tanks has a direct impact on the amount of SWRO capacity required to handle peak demand events. Looking at the different storage options, we have open wet product storage and closed wet product storage, both size around 3,000 to 6,000 cubic meters, depending on whether we plan for 12 or 24 hours of makeup demand. There's also a hybrid conservative product storage option, which is slightly smaller, designed for the same time frames. For raw seawater buffers, we maintain around 1,500 cubic meters for open and closed systems with a 2-hour abstraction buffer. The hybrid raw seawater buffer is a bit smaller, just under 1,000 cubic meters. Our emergency storage philosophy is critical. We aim to have at least 12 to 24 hours of water stored to manage any sudden issues. This is particularly important if the SWRO system or marine water intake is at a higher risk of disruption. Lastly, for systems that need to be concurrently maintainable, like Tier or Rated 3 setups, we incorporate dual or sectionalized tanks, isolation valves, redundant transfer pumps, and maintainable instrumentation for level and quality. This ensures reliability and continuous operation even during maintenance activities. Here, we're looking at the SWRO line routing, which outlines the flow of product, brine, and waste streams within the system. You'll notice that product and reject lines are shown as separate streams to avoid any hydraulic ambiguity, which ensures clarity in how water moves through the process. Starting from the seawater intake, raw seawater is first directed to pretreatment involving ultrafiltration or multimedia filtration to remove larger particles. Then it moves into the SWRO membranes where the reverse osmosis process occurs, separating pure water from the brine concentrate. Post-treatment follows, where the product water is stabilized and adjusted in pH to make it suitable for use. This treated water is then sent to the makeup tank, which supplies the cooling tower and the Batum Coastal Data Center's water needs. On the reject side, we have brine concentrate and RO reject streams that need careful handling. These reject streams, including backwash waste from pretreatment, undergo neutralization, monitoring, and flow metering. Only after meeting strict environmental discharge permit requirements can these combined brine and blowdown streams be safely discharged to the marine outfall. This entire line routing is designed to integrate seawater desalination with the water supply for cooling tower operations and direct liquid cooling, ensuring both operational efficiency and environmental compliance. This slide outlines a makeup water distribution system designed for the Batum Coastal Data Center, focusing on the integration between SWRO desalination, direct liquid cooling, and the cooling tower setup. The treated makeup water from the SWRO product header is directed to each cooling tower through a dedicated metering and control system, which manages 3 types of consumers: open, closed, and hybrid cooling towers, each represented as separate branches. The system starts at the SWRO product tank, which stores low TDS treated water, then moves to the makeup pump set equipped with variable frequency drives for duty and standby operations. From there, the makeup header ensures accurate flow measurement and pressure control. The open cooling tower basin maintains water levels through dedicated controls, while closed cooling tower spray basin monitors both water level and conductivity to maintain optimal conditions. For the hybrid towers, which combine adiabatic pads with wet sump, staged water assistance is provided to optimize cooling efficiency. Additionally, blowdown control is managed by a conductivity-based valve to regulate water quality and prevent scaling. Instrumentation is kept minimal but effective, monitoring critical parameters such as product tank level, pump discharge pressure, flow rate, isolation status of branches, basin levels, conductivity, pH, ORP, or free chlorine/biocide levels, and blowdown flow rates. This setup ensures a balanced water system with real-time monitoring of makeup and blowdown water volumes. When we talk about reject stream management, it's crucial to understand that these streams, like brine, blowdown, and neutralization, aren't just incidental drains. They need to be treated as controlled utilities, engineered carefully to manage their environmental impact effectively. Starting with the brine or concentrate from the SWRO process, this reject has higher salinity, and the flow rate depends on the SWRO recovery. Managing this brine requires dedicated piping that can handle corrosion, precise flow metering, and a thorough outfall study to ensure proper dispersal in the marine environment. Next, cooling tower blowdown is controlled through conductivity to regulate its discharge. It contains chemical residuals from water treatment, so continuous monitoring for pH, temperature, conductivity, corrosion inhibitors, and biocides is essential to keep everything within safe limits. When combining reject streams, it's important to conduct a hydraulic review before mixing them. Proper neutralization and sampling chambers must be included to meet environmental permits and marine dispersion standards. Finally, the engineering design for outfalls must effectively prevent brine from recirculating back into the seawater intake. This involves careful attention to intake and outfall separation, diffuser design, and consideration of environmental factors like ambient currents, tides, and coastal bathymetry to maintain the reliability and sustainability of the SWRO system. In this section, we'll focus on integrated controls, redundancy, and certification. We'll explore how the controls architecture is designed to ensure seamless BMS and DCIM integration, which is crucial for efficient data center operations. We'll also discuss the importance of Tier 3 or Rated 3 readiness, highlighting the standards that guarantee system reliability and uptime. Additionally, we'll cover water usage effectiveness, or WUE, as well as certification requirements that ensure the facility meets environmental and operational benchmarks. The training concept package will provide insights into the Batum Coastal Data Center's unique approach to water supply, including the use of SWRO desalination, direct liquid cooling, and the integration of cooling towers. This holistic approach ensures robust system performance while maintaining sustainability. Let's dive into the controls architecture for the water plant at the Batum Coastal Data Center. The main idea here is that the entire water system, including the seawater reverse osmosis units, cooling distribution units, pumps, and cooling towers, should be managed as one integrated utility rather than as separate, isolated components. This integration ensures seamless operation and better resource management. Our training package focuses on this integration, covering water supply, SWRO desalination, direct liquid cooling, and cooling tower coordination. The control system is visualized through a combination of PLCs, motor control centers, variable frequency drives, and SCADA systems, offering centralized monitoring and control. We utilize various field instruments to measure critical parameters like flow, pressure, differential pressure, level, and water quality. These inputs feed into remote I/O units that manage the SWRO cooling tower and cooling distribution loops. At the heart of the system are programmable logic controllers that handle interlocks and the sequencing of operations, ensuring processes run safely and efficiently. The human-machine interface and SCADA platforms provide trends, alarms, and reports, making it easy for operators to monitor performance in real time. On a higher level, the building management system and data center infrastructure management tools track key performance indicators, helping optimize utility usage. Key interfaces tie everything together. This includes CDU controllers, cooling tower VFDs, SWRO PLCs, MCC and VFD panels, water chemistry analyzers, and the BMS/DCIM systems. The control philosophy centers on linking cooling demand, SWRO production, tank levels, tower makeup, blowdown, pump differential pressure, and water chemistry through a coordinated control sequence. It prioritizes IT cooling continuity above all, ensuring no interruption in service, while simultaneously optimizing water and energy use for efficiency. This integrated approach is fundamental to maintaining reliable and sustainable cooling operations for the data center. This slide focuses on the integrated control system for the Batum Coastal Data Center's water supply, combining SWRO desalination and cooling tower operations. The key is coordinating makeup water production and heat rejection through precise tank level and water chemistry control. Starting with the SWRO trains, they operate based on tank level and water quality, automatically starting or stopping as needed. The product tank functions as both a level and quality buffer, ensuring consistent supply. Makeup pumps regulate pressure and flow to maintain system stability, while the cooling tower basin monitors level and conductivity to optimize performance. The blowdown valve is controlled by conductivity set points to manage water quality within the cooling tower. The normal operating logic activates a duty SWRO train when tank levels fall below a set point, opens a makeup valve when tower basin levels drop, and uses conductivity to control blowdown flow. This coordination enables calculation of cycles of concentration and water use efficiency. In terms of quality control, any off-spec SWRO permeate is diverted to maintain standards, while high conductivity in the tower triggers blowdown to prevent scaling. Low pH or high corrosion index conditions trigger alarms, and chemical dosing is dynamically adjusted based on flow and water quality to protect equipment. Finally, resilience logic enhances system reliability. Standby SWRO trains can start automatically if a duty train trips, and an emergency reserve tank supports short outages. Hybrid cooling towers are capable of switching operating modes depending on ambient conditions and water-saving strategies, ensuring optimized performance under varying circumstances. This integrated control framework is crucial for maintaining water quality, system efficiency, and operational resilience. Instrumentation and metering are absolutely essential for managing water use efficiency and operations effectively. Without accurate metering, it's impossible to manage water use efficiency or water treatment processes with credibility. This slide presents the key components of our training concept package for the Batum Coastal Data Center. It covers everything from the water supply and SWRO desalination to direct liquid cooling and cooling tower integration, emphasizing the importance of controls throughout. Looking at the table, Each location in the water system requires a specific set of instruments to ensure optimal operation. For example, at the seawater intake, instruments like flow, pressure, turbidity, conductivity, and level sensors are critical to monitor the feed water and protect the intake system. Moving to the SWRO pretreatment stage, differential pressure, turbidity, SDI sample, and backwash flow measurements are vital to protect the membranes. In the RO trains, monitoring feed, permeate, and brine flow, along with pressure, conductivity, pH, and temperature, helps ensure recovery rates, water quality, and system performance are maintained. For product tanks, level, conductivity, pH, and residual chemical measurements ensure the water quality remains within acceptable limits. At the makeup header, flow, pressure, and totalizer data are important for controlling water use efficiency and pump operations. In the cooling tower basin, parameters like level, conductivity, pH, and indicators for sanitizers such as ORP, free chlorine, or biocide help manage water chemistry for blowdown and makeup cycles. The blowdown monitoring uses flow, conductivity, pH, and temperature to ensure compliance with regulations and maintain the water balance. In the CDU and TCS cooling loops, monitoring flow, differential pressure, supply and return temperatures, and leak detection are crucial to maintaining reliable direct-to-chip cooling. Finally, the building management system and data center infrastructure management track energy, water usage, alarms, trends, and metrics like water use efficiency and power usage effectiveness to support certification reporting. Overall, each of these instruments plays a specific role in ensuring the water system operates efficiently, reliably, and within compliance standards, making metering foundational to managing the entire water treatment and cooling process effectively. Let's dive into the Tier or Rated 3 readiness, focusing specifically on mechanical and water system redundancy. For a Tier 3 data center, maintaining continuous cooling is critical, and that includes the water system, which must be serviceable without causing any disruption to the IT equipment. First, regarding resilience, the training concept package covers BADM's coastal data center water supply, which integrates SWRO desalination, direct liquid cooling, and cooling towers. This approach ensures a robust and reliable cooling process. For the SWRO and makeup water systems, we implement N+1 redundancy on the SWRO trains, with duty and standby makeup pumps. The system uses dual product tanks or sectionalized storage to ensure continuity. Critical chemical dosing is handled with isolated skids and redundant analyzers monitoring key parameters, minimizing risks from failures. Moving on to cooling towers and hybrid coolers, they operate with N+1 tower cells or modular capacity, and all basin and fan components are designed to be maintainable. The system utilizes dual or sectionalized headers with bypass valves, incorporating electrical feeders managed under an essential power strategy when necessary to further enhance reliability. Regarding CDUs, pumps, and piping, each module has CDU N+1 redundancy and VFD pumps set up with the same redundancy principle. Cooling distribution uses dual headers or a ring main with isolation valves, ensuring no single isolation event removes cooling to any critical IT module. Finally, the concept of concurrent maintainability is fundamental here. It means that any component within capacity or distribution that needs planned maintenance can be isolated or bypassed without disrupting the IT load it serves. This principle guarantees that maintenance activities never interrupt cooling continuity, safeguarding the data center's operation. Here we have the Uptime Certification Path, which outlines a process from design through to operation for achieving Uptime Institute tier certification. An important aspect here is that the water and cooling systems must be accurately reflected in the design documents and then validated during construction to ensure everything aligns with the tier objectives. The training concept package focuses specifically on the BADM Coastal Data Center. It covers critical aspects like water supply, SWRO desalination, direct liquid cooling, and the integration with cooling towers, all of which are essential for the certification process. Looking at the certification types in this table, the first is TCD, or Tier Certification of Design Documents. This involves a thorough design review to confirm the tier requirements are met before construction begins. Then there's TCCF, Tier Certification of Constructed Facility, which is about verifying that the facility as built matches that certified design. Finally, TCOS, Tier Certification of Operational Sustainability, reviews how well the facility is operating over time to ensure it continues to meet the standards. For a Tier 3 design intent, the facility must be concurrently maintainable. This means it includes redundant components and multiple distribution paths, so that maintenance can happen without shutting down IT operations. Regarding the water systems, they must be treated as critical utilities. This involves documenting N+1 redundancy, isolation methods, bypass options, controls, alarms, and maintenance procedures to support reliable operation. One final note on training. The certification body looks at the entire facility objective as a whole. This presentation does not guarantee certification, but highlights the key design provisions that must be incorporated into formal design documents to move towards certification. This slide focuses on the TIA 942 rated 3 design interpretation, specifically related to cooling and water utilities in data centers. Rated 3 emphasizes concurrently maintainable infrastructure, meaning all critical components must support maintenance activities without affecting overall ICT operations. The key concept here is redundancy and multiple independent distribution paths. Although typically only one distribution path is active at a time, others are fully capable of taking over if maintenance or failure occurs. This allows planned maintenance without any interruption to the data center's operations. Regarding cooling utilities, the design includes N+1 redundancy for cooling towers, hybrid cells, pumps, chillers, and cooling distribution units. The system must have isolatable headers and valves, maintainable control panels, analyzers, and power supplies. Additionally, commission failure and maintenance scenarios are essential to ensure reliability. For seawater reverse osmosis, or SWRO provisions, the design incorporates N+1 trains and makeup pumps, a dual storage strategy, and essential backup power for controls and critical pumping. Documented operating procedures for handling water plant outages are also mandatory. An important engineering checkpoint to highlight is that every component in the water path critical for continuous cooling must have a clear maintenance strategy. This includes providing redundant capacity, bypass paths, isolation valves, and well-defined procedures to ensure uninterrupted operation during maintenance or failures. This comprehensive approach supports the high availability and resilience requirements of rated 3 data centers. Water usage effectiveness, or WUE, is a critical metric that ties water demand directly to IT energy consumption, serving as a key indicator of sustainability in our water strategy. Essentially, WUE helps us understand how efficiently water is being used relative to the amount of IT energy consumed. Let's break down the formula and its components. Annual IT energy is calculated by multiplying the IT load in megawatts by the total hours in a year, which is 8,760. For example, with an IT load of 144 megawatts, the annual energy use comes out to over 1.26 million megawatt hours per year. Annual water use, on the other hand, is derived from the daily makeup water demand multiplied by 365 days, then adjusted by an annual operating factor that accounts for peak day demands and operational variations throughout the year. WE itself is then calculated by dividing the annual water usage in cubic meters by the annual IT energy in megawatt hours. This ratio tells us how many liters of water are used per kilowatt hour of IT energy consumption. To put this into context, the green marked data center reference sets thresholds for WE at 2.2 and 2.0 levels, serving as target benchmarks for water efficiency. Meanwhile, LEED certification considers water efficiency credits and metering, where WE can support the narrative, although LEED requirements often focus on specific credit criteria. One important training note is that when reporting WE, it's essential to specify boundary conditions. This includes factors like the type of water source, the cooling technology employed, IT utilization rates, local climate conditions, and whether the water use accounts only for site water or if it includes broader source water impacts. By doing so, we ensure transparency and comparability in water efficiency reporting. In all, understanding and applying WE helps us optimize water use, improve sustainability, and meet industry benchmarks for efficient data center operation. Here we have a comparison of water usage effectiveness, or WE, for different cooling tower alternatives at the Batum Coastal Data Center. WUE is calculated by dividing the peak makeup water usage by the IT energy consumption measured in megawatt hours. Essentially, a lower WUE means better water efficiency. Starting with the open wet cooling tower, we see a peak makeup water use of around 6,446 cubic meters per day, resulting in a WUE of 1.87 cubic meters per megawatt hour. This serves as our baseline for comparison. The closed wet system uses a similar amount of water, about 6,444 cubic meters per day, but offers a slightly better WUE of 1.86. While the water savings here are minimal, the closed wet system improves loop cleanliness and makes maintenance easier. The hybrid options present more significant water savings. The hybrid optimized system uses only 2,900 cubic meters per day, cutting the WUE down to 0.84. This represents a strong case for water conservation, making it the most efficient option in terms of water use. The hybrid conservative option uses more water than the optimized version at 4,188 cubic meters per day, yielding a WUE of 1.21. This approach offers a moderate water-saving benefit, balancing efficiency with operational conservatism. For certifications like LEED or Green Mark, the hybrid systems, especially the optimized one, are the strongest pathways to reduce water use effectively. While the closed wet system enhances cleanliness and maintainability, it shouldn't be considered a major water-saving strategy on its own. Overall, choosing the right cooling tower setup can make a substantial impact on both water consumption and facility performance. Here we focus on green building certification, specifically related to water efficiency in data centers. Certifications like LEED and Green Mark emphasize measurable sustainability features, not just engineering utilities. This means the water strategy must demonstrate real, trackable benefits. Key to this is a comprehensive training concept package, especially relevant to the Badham Coastal Data Center, covering water supply, seawater reverse osmosis desalination, direct liquid cooling, and integration with cooling towers. Looking at certification objectives, LEED Gold and Platinum prioritize water efficiency alongside energy and atmosphere credits. To achieve this, permanent metering, cooling tower water management, narratives on alternative water sources, and understanding energy-water trade-offs are essential. For BCMDA Green Mark certification, tracking water use efficiency, water metering, and sustainable operation strategies are critical. Design records must include detailed calculation sheets and metering plans, establishing baselines for water use efficiency, and documenting meter data for makeup water, blowdown, SWRO production, and cooling tower chemistry. Functional commissioning tests are equally important to verify that systems like SWRO failover and cooling tower controls operate correctly. Ongoing certification success relies heavily on monthly reporting via KPIs covering water, energy, water use efficiency, chemical use, and system performance indicators like alarms and downtime. Ultimately, documentation is the cornerstone of certification success. This means detailed design records, properly installed and calibrated metering devices, commissioning evidence, and thorough operational records must all be maintained consistently. Without this solid documentation foundation, achieving and maintaining certification becomes much more difficult. Here we have the reliability matrix for the critical water and cooling systems of the Badham Coastal Data Center. This matrix translates the Tier 3 design intent into practical design provisions that ensure the plant remains reliable and maintainable. Starting with the seawater intake, the design includes dual pumps and maintainable screens, along with bypass and isolation capabilities. This setup allows for intake well cleaning without shutting down the entire plant, which is essential to avoid downtime. For the SWRO, or seawater reverse osmosis trains, there's an N+1 configuration with isolation valves and independent flushing and cleaning in place. This means even if one train is offline, production can continue uninterrupted. Product storage involves dual or sectionalized tanks, so one tank can be isolated for maintenance while the other continues to supply water, ensuring continuous availability. The makeup pumps are designed with N+1 variable frequency drives and dual power sources where necessary, allowing pump maintenance without losing the makeup water supply. Cooling towers follow an N+1 setup for cells, fans, and pumps with isolatable basins. This means maintenance can be performed on one cell, while the cooling process continues unabated. Cooling distribution units, or CDUs, are duplicated per module with unit failover capabilities. This guarantees that even if one CDU fails in a module, there is no impact on IT operations. Finally, the control systems incorporate redundant critical sensors, uninterruptible power supplies, and backup PLC strategies. This ensures that no single sensor failure will cause unsafe operation. Overall, this reliability matrix ensures that every critical component has redundancy and maintainability designed in, supporting continuous, resilient operation of the water and cooling systems. Let's delve into the key operational and maintenance KPIs for water and liquid cooling systems in a high-density liquid-cooled data center. These facilities require daily tracking of water usage and thermal performance to ensure efficient and reliable operation. Starting with daily water KPIs, we monitor crucial metrics like the production volume of seawater reverse osmosis, or SWRO, measured in cubic meters per day. We also track the amount of makeup water added to the cooling towers, blowdown volumes, and key water quality parameters such as cycles of concentration, conductivity, pH, and oxidation reduction potential. Importantly, water usage effectiveness, or WUE, is calculated on a rolling 7-day basis, as well as monthly to identify trends and opportunities for improvement. On the thermal side, we focus on heat transfer performance at the cooling distribution unit in megawatts, supply and return temperatures at various points, such as a thermal control system and freshwater system, and the cooling tower approach temperature, which indicates how efficiently heat is being rejected to the atmosphere. Additionally, we evaluate chiller efficiency through kilowatts per ton of cooling or the coefficient of performance. Reliability KPIs include assessing the available redundant capacity to ensure system resilience, monitoring active and suppressed alarms, counting the number of starts for trains, cells, and pumps, tracking the cleaning in-place intervals and membrane performance for the desalination system, and recording any leak detection events. A critical training note highlights that water usage effectiveness must be actively managed through metering, consistent reporting, and continuous optimization. This is not simply a design calculation done once, but an ongoing operational responsibility to maintain optimal performance and sustainability. Here we have a full schematic overview of the Batum Coastal Data Center's water supply and cooling system, focusing on the integration of SWRO desalination, direct liquid cooling, and cooling towers. The campus consists of 6 modules, each delivering 24 megawatts of IT capacity. Each of these modules is equipped with its own N+1 cooling system to ensure reliability. The entire campus shares a common SWRO utility, which includes 5 trains for operational duty trains, and 1 is on standby for redundancy. This shared SWRO plant provides treated makeup water, stored in 2 large product tanks, each holding 3,500 cubic meters. This centralized design avoids duplicating water plants in each module. Makeup water is distributed via a metered header system across the campus, ensuring precise control and monitoring. Within each 24 megawatts IT module, we have an N+1 configuration, including 10 CDUs installed with 9 duty units and 1 standby, 5 heat rejection pumps set up as 4 duty and 1 standby, cooling tower cells designed with N+1 redundancy by block, and chillers selected to vendor-specified N+1 criteria. This setup is replicated consistently across all 6 modules, maintaining uniform reliability standards. Additionally, tower blowdown and SWRO brine are managed carefully, with controlled neutralization and monitoring to handle waste outfall responsibly. Color coding in the schematic helps differentiate systems. Teal indicates SWRO makeup water. Green represents the IT secondary coolant path. Blue marks the primary facility water path. Orange shows the air cooling residual paths, and red outlines controlled reject streams. Overall, the campus incorporates 60 CDUs, with 54 operating and 6 as standby units, alongside 30 heat rejection pumps. Cooling tower cells number at least 17, selected based on thermal requirements, while residual air chillers are specified by the vendor. This comprehensive, redundant water and cooling architecture ensures high availability and efficient thermal management for the data center. On this slide, We're focusing on equipment visuals designed to support vendor-neutral, real equipment style training. This approach uses representative imagery that helps make engineering concepts easier to understand without tying them to any specific manufacturer, which is crucial for broad applicability. The training package centers around the Batum Coastal Data Center, covering key systems like water supply, seawater reverse osmosis desalination, direct liquid cooling, and integration with cooling towers. The equipment visuals are categorized to clarify their functions and relationships within the system. We highlight various pieces of equipment, such as high-capacity chilled water distribution units, liquid-to-liquid heat exchangers, different types of cooling towers, including open wet, direct contact evaporative, closed wet tower with closed coil plus spray loop, and hybrid adiabatic cooling systems with dry and stage wet assist. Additionally, the visuals include water-cooled chillers, residual air pack condensers, facility pumps for primary loop circulation, IT racks with direct-to-chip cold plates, and CRH or fan wall units handling residual air cooling. On the water production side, we feature the SWRO plant for makeup water production, side stream filters for tower solids control, and chemical dosing skids for water treatment. The key takeaway here is that the visual board distinctly separates heat transfer equipment, pumping equipment, water production units, and tower water treatment components. This organization makes the overall campus schematic more readable and helps engineers more effectively link their calculations to the actual physical systems they work with. Here we have the CDU capacity schedule, which is organized both at the campus level and per individual module. The sizing is based on a 2.3 megawatt class CDU capacity with an N+1 redundancy for each 24 megawatt module to ensure reliability. Starting with the module's direct liquid load, it's set at 19.2 megawatts, which is 80% of the 24 megawatts capacity per module. To handle this load, 9 duty CDUs are required, calculated by dividing 19.2 by 2.3 and rounding up. However, to maintain N+1 redundancy, we install 10 CDUs per module. Since the campus includes 6 such modules, the total number of installed CDUs is 60. Regarding flow rates, each CDU handles a secondary flow of approximately 198 cubic meters per hour within the thermal cooling system loop, and a primary flow of about 247 cubic meters per hour in the facility's water loop. This scheduling ensures the cooling system is both robust and efficient, integrating seamlessly with the water supply and cooling infrastructure, including the SWRO desalination and cooling tower systems, which are critical for the Batum Coastal Data Center environment. Here, we're diving into the key control points and alarms involved in managing the CDU or cooling distribution unit. The CDU's integration is crucial for maintaining thermal stability, protecting against leaks, and ensuring smooth coordination between units, which is essential for reliable operation. Let's walk through the main control points outlined in the table. First, the secondary supply temperature is regulated using PID control to keep the IT coolant supply within the required class. This is vital for consistent thermal management of the IT equipment. Next, secondary differential pressure flow is managed through VFD pump control, which ensures proper coolant flow to racks and cold plates, maintaining efficient cooling. The primary valve and flow are adjusted by capacity control to match the heat transfer load of the CDU, optimizing energy use and cooling performance. Leak detection acts as a safety mechanism, triggering alarms or even shutdown sequences to protect both the IT equipment and the surrounding white space from damage. Filter differential pressure is monitored to signal when maintenance is needed, protecting the cold plates by ensuring filters remain effective. Conductivity and chemistry parameters are continuously monitored for fluid quality assurance, helping prevent corrosion or contamination. Finally, unit failover is handled through group control, supporting N+1 operation to maintain system reliability and escalate alarms as needed. On top of these control points, the training concept package covers an integrated approach involving Batum Coastal Data Center water supply, SWRO desalination, direct liquid cooling, and cooling tower integration, demonstrating a comprehensive strategy for effective CDU management. Here we have the pump schedule for the condenser and facility water systems at our Batum Coastal Data Center. The pump configuration follows a modular N+1 arrangement, which means for every module, there are 4 pumps running and 1 standby pump ready to take over if needed. This setup ensures that maintenance can happen without interrupting cooling operations, supporting continuous reliability. Looking at the numbers, the total tower water flow for the entire campus is around 16,297 cubic meters per hour, designed to support a cooling load of 151.6 megawatts with an 8 Kelvin temperature difference. This flow is divided equally among 6 modules, each handling approximately 2,716 cubic meters per hour. Within each module, the pump arrangement includes those 4 duty pumps plus the 1 standby, all typically running at roughly 700 cubic meters per hour. Altogether, across the campus, there are 30 pumps installed, aligned with the 6 modules. For control, we use variable frequency drives with differential pressure control. This means pump speed adjusts dynamically based on valve position, optimizing pressure and energy usage throughout the system. This combination of modularity, redundancy, and smart control is key to maintaining efficient, reliable cooling for the data center. Here we have the chilled water pump schedule specifically designed for residual air cooling. This loop plays a crucial role in supporting the CRH and FW coils, as well as managing the residual heat generated in the data hall. The training concept package focuses on the Batum Coastal Data Center, integrating water supply through SWRO desalination, direct liquid cooling, and cooling tower systems to optimize efficiency. Looking at the table, the residual airside heat is estimated at 28.8 megawatts, which accounts for about 20% of the total IT load across the campus. The chilled water temperature differential, or delta T, is set at 8 Kelvin, falling within the conceptual design range for the campus. To handle this, the total chilled water flow required is calculated to be approximately 3,096 cubic meters per hour. When we break this down per module, assuming 6 modules of the campus, each module requires around 516 cubic meters per hour of chilled water flow. For each module, the pump configuration follows an N+1 redundancy, meaning each set includes 2 pumps running in duty and 1 pump on standby. Each pump is expected to handle about 300 cubic meters per hour. So together, the 2 duty pumps provide around 600 cubic meters per hour for efficient and reliable operation. This setup ensures robust cooling performance and system reliability for the data center. Let's talk to the tower cell schedule and how we select cooling tower cells. The final tower selection isn't just about meeting a heat load number. It requires a detailed thermal selection process conducted by the manufacturer, specifically tailored for Batum's weather conditions. This ensures that the tower performs efficiently in the local climate. The training concept package we're using covers Batum's coastal data center water supply, SWRO desalination, direct liquid cooling, and integration with the cooling towers. It's a comprehensive approach designed for optimal performance. Looking at the table, our heat rejection basis is 151.6 megawatts, which combines the direct facility loop and the chiller condenser load. We've estimated an example tower cell capacity at 10 megawatts per cell as a placeholder for training purposes. Dividing the total heat rejection by the cell capacity gives us 16 duty cells. However, to build in redundancy and ensure reliability, the installed cells will be duty cells plus an additional 1 or follow an N+1 configuration per plant block, so about 17 or more cells. It's important to note that cooling towers come in different types, open, closed, and hybrid, and while they handle the same heat duty, they vary significantly in terms of physical footprint, fan operations, and water behavior. The rated or tier. 3 implications mean any cell, pump, or variable frequency drive can be maintained without losing IT cooling capacity during planned maintenance, which is crucial for data center uptime. Finally, a critical note: never finalize a cell count based solely on megawatts. You must use manufacturer software that factors in design wet bulb and dry bulb temperatures, approach, range, altitude, acoustics, plume, redundancy, and water-saving modes. This comprehensive evaluation ensures the cooling tower system is both efficient and reliable under all operational conditions. Let's take a closer look at water quality and its importance in different parts of our system. Here, we have several distinct water classes, each with its own quality requirements because they serve different functions. First, The SWRO product or tower makeup water needs to have low total dissolved solids, low turbidity, and controlled pH. This is essential because it feeds the cooling tower basin and needs to be compatible with the tower's chemical treatment program. Next, the cooling tower circulating water naturally has higher TDS due to cycles of concentration, but is carefully treated to prevent corrosion, scaling, and microbial growth. This water is open to the atmosphere, circulating through the tower basin and spray loops. For the facility water loop, we typically use a closed system with treated water or a glycol mixture, depending on the topology. This loop supports the primary cooling distribution unit and chiller or tower heat exchanger loops, maintaining efficient heat exchange while preventing contamination. The TCS secondary coolant must be an OEM-approved treated water or propylene glycol mixture. It's clean, filtered, inhibited, degassed, and constantly monitored to ensure optimal performance and protection of the system components. Finally, immersion fluids, which are dielectric fluids, are only necessary if immersion cooling is used. They are not part of this direct-to-chip cooling concept, so they're not relevant here. Additionally, it's important to note the training concept package integrates knowledge of the Batum Coastal Data Center's water supply, SWRO desalination, direct liquid cooling, and cooling tower integration, ensuring all aspects of water quality management are covered thoroughly. Let's talk about water safety in cooling towers, focusing on cooling tower water safety and biological control. Even when the makeup water comes from a seawater reverse osmosis or SWRO system, it doesn't eliminate biological risks. Instead, it changes the baseline chemistry of the water. This makes ongoing management critical. Our training concept package uses data from the Batum Coastal Data Center's water supply, which includes SWRO desalination, direct liquid cooling, and how these integrate with the cooling tower. Understanding the water quality is fundamental for effective management. Key safety controls include a comprehensive cooling tower water management plan, combined with biocide treatments and corrosion or scale inhibitor programs. Routine sampling and microbiological monitoring are essential to keep the system safe, alongside regular maintenance of drift eliminators and basin cleaning to prevent contamination and buildup. Instrumentation plays a vital role in monitoring parameters like pH, conductivity, oxidation reduction potential, or ORP, and free chlorine or other biocide indicators. We also monitor makeup and blowdown flow meters, temperature, and basin levels, using automated systems for blowdown and dosing interlocks to maintain optimal conditions. On the operations side, it's crucial to maintain the target cycles of concentration, or COC, without allowing scaling to occur. All chemical adjustments should be carefully documented. Ensuring safe access to the tower for maintenance is a must, and integrating alarms into the building management system or data center infrastructure management helps quickly identify any issues. Finally, a key training note. While low total dissolved solids, or TDS, makeup water can allow higher cycles of concentration, low alkalinity water may be more corrosive if it's not properly stabilized. This means water treatment specialists must review and guide the process to avoid problems. This comprehensive approach ensures both safety and efficiency in cooling tower water management. In this section, we'll focus on cooling tower chemical treatment and side stream filtration, which are critical for maintaining system efficiency and longevity. We'll cover key topics such as exposure to open circuit water, protecting the closed circuit loop, and the overall filtration strategy. Understanding the chemical treatment program is essential, as it directly affects operational costs and the required instrumentation for monitoring and control. Additionally, we'll explore a training concept package tailored for the Batum Coastal Data Center, including its water supply methods like SWRO desalination, direct liquid cooling, and how these integrate with the cooling tower system. This comprehensive approach ensures we manage water quality effectively and optimize cooling tower performance. Let's talk about chemical treatment in open circuit cooling towers. Since these towers expose circulating water directly to the air, it's crucial to actively manage several factors, including scale, corrosion, biological growth, suspended solids, and conductivity. The primary goal here is to maintain optimal heat transfer efficiency and protect the cooling system components. To achieve this, we use a chemical dosing skid that delivers inhibitors, biocides, pH trim agents, and dispersants. These chemicals serve specific purposes. Antiscalants and dispersants help control scale formation. Corrosion inhibitors and pH adjusters protect the basin, piping, heat exchangers, and pumps, while biocides keep microbiological growth like biofilm and Legionella risk under control. Another essential control is managing the conductivity or cycles of concentration through automated blowdown, which balances water conservation with the risk of scaling and corrosion. Suspended solids are addressed with side stream filtration and basin sweeping to reduce fouling, sludge buildup, and associated corrosion risks. In summary, chemical treatment and proper filtration aren't optional. They are fundamental to the health and efficiency of an open cooling tower system. Neglecting these processes leads to higher fouling rates, increased chemical use, more frequent blowdowns, greater biological risks, increased cleaning, and higher energy consumption for fans, pumps, and chillers. This training is based on recognized cooling tower management guides, which emphasize cycles of concentration and blowdown control as key strategies for water efficiency. Side stream filtration is widely used to continuously remove suspended solids, thereby enhancing overall water treatment performance. Let's talk about side stream filtration and its role in open circuit cooling tower water systems. Side stream filtration continuously cleans a portion of the recirculating tower water, typically about 5 to 10% of the total circulating flow. This percentage is initially set based on design, but is then fine-tuned by monitoring water quality and solids loading to ensure optimal performance. In our Batum Coastal Data Center project, where we integrate seawater reverse osmosis desalination, direct liquid cooling, and cooling towers, the side stream filter plays a crucial role. The filter skid can be configured using media, separators, or cartridges depending on the final design requirements. Sizing is straightforward but essential. For example, with a campus open wet recirculation flow of around 16,300 cubic meters per hour, a 5% side stream filter handles about 815 cubic meters per hour, while 10% filters about 1,630 cubic meters per hour. For a 24 megawatt module with a circulation flow of roughly 2,700 cubic meters per hour, the filter flow range falls between 136 to 272 cubic meters per hour. The benefits of side stream filtration are significant. It reduces suspended solids, which means less sludge buildup in the basin, less fouling, and clearer water overall. This leads to cleaner heat transfer surfaces, which improves efficiency by reducing approach temperature degradation and lowering the associated energy penalty. Additionally, a cleaner system makes biocides more effective and limits biofilm formation, as well as microbiological nutrient load. With better control of cycles of concentration, filtration supports higher cycles when chemistry and scaling limits allow, leading to a more stable operation. Maintenance and operational burdens are also reduced, thanks to less frequent cleaning requirements and fewer unplanned manual basin cleanings. Regarding installation, the preferred connection points for the side stream filter are from the cooling tower basin or the condenser water return or header. From there, water flows to the filter skid and back to the basin via sweeping nozzles or controlled return header. It's critical to include isolation valves, bypass options, differential pressure monitoring, backwash drains, and turbidity or solids monitoring whenever possible. Importantly, side stream filtration is not a substitute for chemical treatment. Instead, it enhances the water environment so chemical programs can operate more effectively, reducing the risk of fouling and improving overall system health. This combination of mechanical and chemical treatment ensures long-term operational efficiency and reliability. Let's examine the operational expenditure, or OPEX, impact when choosing between open and closed-circuit cooling towers and water treatment systems. Closed-circuit towers don't significantly reduce evaporation compared to open circuits, so water savings aren't substantial. However, they do offer important benefits by reducing contamination in the facility loop, lowering the cleaning requirements, and decreasing the risk of fouling in critical heat exchangers. In an open wet tower, the tower water is directly part of the facility loop and is exposed to air and solids, which means you need spray and basin treatment, side stream filtration, chemical dosing, and continuous monitoring. These factors lead to higher OPEX due to increased cleaning, chemical use, filtration needs, and biological control efforts. On the other hand, Closed wet towers keep the facility water inside a closed coil, protecting it from direct exposure. This setup strongly recommends side stream filtration primarily for the spray basin, while a facility loop can rely on closed loop filtration, reducing the fouling risk. Accordingly, the overall facility loop OPEX is lower, although you still have OPEX related to the spray loop. Regarding water use, both systems experience evaporation, blowdown, and drift, so closed-circuit towers don't offer significant water savings. For mission-critical data centers, like the Batum Coastal Data Center with its SWRO desalination, direct liquid cooling, and cooling tower integration, it's best to evaluate closed-circuit or hybrid closed adiabatic options by considering not only water use, but also factors like heat exchanger cleanliness, maintenance exposure, biological risk, filtration requirements, and the operational staffing needed to maintain the system effectively. This comprehensive approach will help optimize both performance and costs. This slide outlines a treatment architecture for Batum Coastal Data Center's water supply system, focusing on seawater reverse osmosis desalination, direct liquid cooling, and the integration of cooling towers. The core of this design revolves around side stream filtration on the cooling tower, offering two main options. Option 1 involves taking a side stream of about 5 to 10% from the hot condenser water return. This side stream is filtered and then returned directly to the hot return line before entering the tower. The goal here is to remove impurities before the water circulates further, ensuring system efficiency. Option 2 uses a closed local polishing loop within the cooling tower basin itself. In this arrangement, basin water is circulated through the filter and then returned back to the basin. This approach continuously cleans the water inside the tower while keeping the system closed locally. For both options, all dirty drains and blowdown water are routed through a neutralization process before discharge. This includes a filter backwash and tower blowdown, which enter a neutralization tank, where pH is carefully monitored and controlled using acid or alkali dosing to meet the local wastewater discharge standards. The neutralized wastewater is then safely discharged to the city drainage system. From an operational perspective, the system includes automated controls, such as automatic drain valves triggered by differential pressure or timers, and a building management system that monitors parameters like differential pressure, valve positions, pH levels, flow rates, conductivity, and turbidity to maintain optimal performance. Finally, the sizing for these options uses the actual condenser water circulation flow, applying a logic of filtering between 5 and 10% of this flow in the side stream filter skid. The combination of precise filtration, chemical dosing, and monitoring ensures the water system runs efficiently while complying with environmental regulations. Let's focus on the electrical and MCC architecture for the water and cooling utility systems, which are critical components in ensuring the availability and reliability of these systems. First, it's important to integrate key water and cooling equipment into the overall design to avoid any downtime or failures. Our training concept package, specifically tailored for the Batum Coastal Data Center, includes comprehensive coverage of water supply, SWRO desalination, direct liquid cooling, and cooling tower integration. On the electrical side, we look at the MCC, PLC, and VFD lineup. These components play a vital role in the electrical control, pumps, cooling towers, SWRO units, and various instrumentation throughout the facility. The MCC sections cover several critical equipment groups: SWRO intake and high-pressure pumps, makeup and tower pumps, tower fan, and blowdown valves, along with facility water, chilled water, and condenser pumps. All these are controlled and monitored via analyzers, PLCs, network systems, and UPS-backed instruments to ensure continuous operation. Our Tier 3 electrical strategy is designed to maintain control continuity and stable water production by coordinating essential power sources, preventing common mode failures in MCC, VFD, and control power systems, and providing maintenance bypasses or isolation options where necessary. Finally, the design output should be thorough and detailed, including a single-line diagram, load lists, VFD lists, cable schedules, earthing plans, lightning protection, harmonic studies, and a power law sequence. This comprehensive documentation ensures the system is robust, maintainable, and ready for any operational challenges. Now, let's discuss commissioning and performance tests, which are crucial for ensuring the system meets its design and operational goals. Commissioning involves validating key aspects like calculations, controls, water balance, and redundancy to confirm everything functions as intended. Our training concept package focuses specifically on the Batum Coastal Data Center's water supply, incorporating SWRO desalination, direct liquid cooling, and cooling tower integration. Looking at the test areas in detail. First, the SWRO SAT test checks net production, recovery rates, permeate TDS levels, brine flow, and alarm functions to prove the makeup plant's capacity. Next, tower performance testing verifies heat rejection by assessing approach and range, fan and pump control, wet and dry modes, and blowdown control. The CDU test ensures liquid cooling continuity by validating load transfer, secondary flow and differential pressure, leak detection, and failover capabilities. For the pumps, we test flow rates, head, variable frequency drive turn down, and standby start to prove reliable hydronic distribution. Controls factory performance testing confirms integration by validating tank level logic, quality divert, mode switching, and alarm escalation. Tier and rated demonstrations focus on planned maintenance of critical components like train, pump, tower cell, and CDU path to prove concurrent maintainability. Finally, water use efficiency reporting through meter totalization and monthly reporting helps verify sustainability metrics. Together, these commissioning tests provide comprehensive assurance that all systems perform safely, efficiently, and as designed. Here we have an overview of the key risks associated with our project, along with their mitigation strategies. The main risks we're focusing on include water security, corrosion, fouling, control integration, and certification evidence. Starting with marine intake fouling, this risk is rated as high severity. To combat this, we're implementing screens, dual pumps, cleanable piping systems, and continuous intake monitoring to ensure the system remains clear and efficient. For brine recirculation, which is also a high risk, measures like hydrodynamic studies and careful intake and outfall separation using diffuser designs help minimize potential problems. When it comes to tower scaling and corrosion, we're controlling the cycle concentration, stabilizing pH levels, applying targeted treatment programs, and using online monitoring tools to detect issues early. The risk of coolant contamination in the cooling distribution units is similarly high, so we designed a separate cooling loop with filtration and chemical monitoring, along with leak management protocols, to keep the system clean and reliable. Hybrid system underperformance carries a medium to high risk, so we're using hourly weather simulations, developing contingency plans for all wet scenarios, and employing a temperature reset strategy to optimize performance. For water use efficiency underreporting, considered a medium risk, we're installing permanent meters and integrating monitoring into the building management and data center infrastructure management systems to ensure accurate reporting. Lastly, the certification gap is a high-risk area. To address this, we're maintaining thorough design documentation, develop maintainability diagrams, and keep detailed commissioning records to provide clear evidence for certification. This comprehensive approach within the training concept package, covering coastal data center water supply, SWRO desalination, direct liquid cooling, and cooling tower integration, ensures that we proactively manage risks and maintain system reliability. Let's look at the key commercial drivers for this project. When considering capital expenditures or CAPEX, it's important to evaluate costs in relation to water security, water use efficiency, energy consumption, ongoing maintenance, and certification values. These factors all influence the total investment value. Specifically, CAPEX drivers include things like the type of cooling tower selected and its footprint, the capacity and redundancy of the seawater reverse osmosis or SWRO system, the marine intake and outfall works, as well as storage tanks, pump systems, and the necessary control, metering, and chemistry monitoring systems. On the operational side, or OPX, the main costs stem from the energy needed to run cooling tower fans and pumps, the electricity used per cubic meter of water treated by the SWRO system, membrane life, chemical treatment requirements, handling of blowdown and discharge, and maintenance labor and spare parts. Decision-making also depends heavily on external factors like water availability and tariffs, environmental permitting risks, the water use efficiency targets, evidence for uptime as per TIA standards, and anticipated future AI load growth. In conclusion, Using a hybrid closed adiabatic cooling tower may add some mechanical complexity and take up more space, but also has potential to significantly reduce both makeup water requirements and SWRO system size. This approach should be carefully validated against BATM's local weather conditions and the IT liquid temperature targets to ensure optimal performance. Here we have an overview of the key design deliverables recommended for the upcoming engineering phase. These documents are essential because they transform our initial concept into a fully certifiable design package. First, the training concept package covers critical systems specific to the BATM Coastal Data Center. This includes a water supply, SWRO desalination process, direct liquid cooling, and the integration of the cooling tower. It's important that everyone involved understands these elements clearly as they form the foundation of our design. Now, looking at the table, let's break down each deliverable and its minimum content. The design basis report should cover the IT load demands, how cooling loads are split, water balance calculations, water use efficiency, and our redundancy philosophy to ensure reliability. Next, the PFDs and PNIDS must detail the seawater reverse osmosis system, makeup water supplies, cooling towers, cooling distribution units, and all reject streams to fully map out the fluid flows. The hydraulic model will validate pipe sizing, pump head requirements, net positive suction head, surge conditions, and valve authority, which are all critical to system stability and efficiency. For thermal modeling, we'll incorporate hourly weather data, select appropriate cooling towers, define the hybrid wet fraction, and analyze water versus energy trade-offs to optimize performance. Water quality specifications will set the standard for tower makeup water, circulating water, facility water, and the cooling system coolant, ensuring all fluids meet necessary quality levels. The controls narrative will describe cause and effect scenarios, include the input-output list, alarm matrix, and outline building management system, and data center infrastructure management points. Certification matrix documentation will verify that the design complies with uptime requirements like TIA standards, as well as sustainability certifications, such as LEED and Green Mark. Finally, the commissioning plan defines the steps for site acceptance testing, factory performance testing, integrated system tests, and demonstration of maintainability, ensuring the design operates as intended after installation. Together, these deliverables provide a comprehensive framework to move from concept to a fully engineered, certifiable solution. This slide outlines a recommended agenda for our upcoming engineering workshop, which is critical for aligning all stakeholders before we move into detailed design. The focus will be on the BATM Coastal Data Center project and covers key elements such as a water supply, seawater reverse osmosis desalination system, direct liquid cooling, and the integration of cooling towers. The next steps are clearly defined to ensure we cover all essential technical decisions. First, we need to confirm the IT load and how the liquid cooling will be split across each deployment phase, which is fundamental for capacity planning. Then, we'll verify the cooling distribution unit capacity, its location, and the architecture for the rack manifold to optimize efficiency. We must also decide on the type of cooling tower, whether it will be open, closed, or a hybrid closed adiabatic system, as this impact performance and sustainability. Setting the water usage efficiency target and aligning with Green Mark or LEED certification strategies is a priority to meet our environmental goals. Our seawater reverse osmosis system sizing needs to be established, determining if we design for normal operational conditions only or include contingency coverage for resilience. Agreeing on tier or rated. 3 maintainability diagrams for all water and cooling utilities will ensure high reliability and maintainability standards. Defining clear water quality boundaries and coolant specifications is crucial to protect equipment and maximize lifespan. Finally, we'll set up metering and integrate it with the building management system and data center infrastructure management tools, as well as standardize the monthly reporting format to track performance effectively. This comprehensive agenda will help us address all critical components systematically, ensuring a well-coordinated execution strategy. Let's review the core lessons from our training focused on the BATM Coastal Data Center's water supply and cooling strategy. First, regarding cooling. Cooling distribution units transfer heat, while cooling towers or hybrid coolers are used to reject that heat. However, Even after this process, there is still residual heat in the air that requires additional handling with CRH units, fan wall units, and chiller capacity to maintain optimal temperatures. Interestingly, open and closed wet cooling towers have comparable evaporated water demands when operating at the same duty. Turning to water considerations, the sizing of the seawater reverse osmosis, or SWRO system, must align precisely with the makeup water requirements of the cooling towers. It's important to manage brine and blowdown as separate, control reject streams to maintain system efficiency. Notably, hybrid operation serves as the primary method for saving water, making it a key strategy for sustainability. On certification, it's essential that water usage effectiveness is both metered accurately and reported transparently. 4-tier or rated 3 data centers, concurrently maintainable water, and cooling utilities are mandatory. Equally important are thorough design documents and commissioning evidence. These are just as critical as the physical equipment itself in meeting compliance. Finally, our recommendation for the BADM liquid-cooled campus is to focus on 2 water strategies for engineering comparison. Use a closed wet system as a reliability baseline, since it offers consistent performance, while a hybrid closed adiabatic system should be considered as the water usage effectiveness and water security alternative. Although an open wet system remains a viable cost baseline option, it presents higher risks of contamination, which must be carefully weighed. These key takeaways will guide us toward efficient, reliable, and sustainable cooling and water management for the data center. Here, we provide a comprehensive list of references that have informed the assumptions, calculations, terminology, and certification requirements presented throughout this training concept package for the BADM Coastal Data Center. These references cover a broad range of topics critical to water supply strategy, including seawater reverse osmosis desalination, direct liquid cooling, and cooling tower integration. Starting with the cooling tower water balance, the key factors involved are makeup water, which accounts for evaporation, blowdown, and drift. We also highlight the importance of cycles of concentration, which is a ratio of dissolved solids in tower water compared to the makeup water. Regarding water efficiency, we drew on authoritative sources, such as the EPA and Energy Star Mechanical Systems Water Efficiency Guide, along with the DOE's Federal Energy Management Program best practices for cooling tower management. For side stream filtration, we reference DOE guidelines, ASHRA technical articles specifying typical filtration flow fractions, and original equipment manufacturer recommendations, all pointing to a side stream flow rate of around 5 to 10%. In terms of cooling tower water treatment, our references cover best practices for controlling scale, corrosion, biological growth, pH levels, conductivity, and managing blowdown to maintain system integrity. For data center certification guidance, materials like the Uptime Institute Tier 3 Standard, TCDD, TCCF Pathways, and the TI 942 rated 3 requirements for concurrent maintainability were essential to define benchmarks. The liquid cooling component relies on manufacturer data for high-capacity cooling distribution units, used here strictly as anonymous capacity references to inform training sizing, without endorsing any specific brand. Lastly, any equipment visuals included in this presentation serve purely for engineering training and conceptual discussions. They remain neutral, not advocating for any particular vendor or product choice. This ensures clarity and focus on the technical concepts rather than commercial considerations. Now we're moving into section 06, which is the appendix focused on calculation details. Here, we'll delve into the specific formula checkpoints and design matrices that are essential for engineering training. This section provides a technical backbone needed to understand and apply the concepts we've discussed. The training package centers around the BADM Coastal Data Center's water supply, covering key processes such as seawater reverse osmosis desalination, direct liquid cooling, and the integration of cooling towers. This detailed information will help ensure accurate design and operational efficiency in these complex systems. In this appendix, we focus on essential heat balance formulas that are crucial for engineers working with cooling systems. One of the key points is the formula Q equals M times Cp times delta T. This is fundamental for calculating heat transfer in all liquid loops. Here, Q represents the heat transfer rate, M is the mass flow rate, Cp is the specific heat capacity, and delta T is the temperature difference. For water specifically, we use a volumetric flow rate formula. V in cubic meters per hour equals Q in kilowatts multiplied by 0.86 divided by delta T in Kelvin. The 0.86 factor is derived from typical values for water's specific heat capacity and density, making these calculations more straightforward. This training package covers the Badham Coastal Data Center's water supply system, incorporating seawater reverse osmosis desalination, direct liquid cooling, and cooling tower integration. Understanding these heat balance principles is key to optimizing these complex cooling processes effectively. You'll also notice representative visuals and equipment images included to help illustrate these concepts further and support practical understanding. Here in Appendix B, we focus on the CDU calculation checkpoint, which is essential for our engineers' detailed training. The training concept package covers critical systems for the Badham Coastal Data Center, including the water supply, SWRO desalination, direct liquid cooling, and the integration with cooling towers. One of the key points is a calculation of the direct liquid load, which comes out to 144 megawatts multiplied by 80%, giving us 115.2 megawatts. Based on this load, if we use a centralized CDU system, the number of duty units required is calculated by dividing 115.2 by 2.3 megawatts per unit and rounding up, resulting in 51 units. However, to improve maintainability, we've adopted a module approach, which means installing 60 units instead. This gives us better flexibility and ensures smoother operations without compromising performance. On this slide, we are looking at Appendix C, which focuses on the TCS flow checkpoint. This section serves as a detailed training note specifically designed for engineers. The main training concept package covers several critical components: the Badham Coastal Data Center's water supply, seawater reverse osmosis desalination, direct liquid cooling, and the integration of cooling towers. These elements are essential for understanding how the cooling systems are designed and managed in this facility. One of the key points to note is the calculation of flow rates. The total flow volume, V, is calculated as 115,200 kilowatts multiplied by 0.86 divided by 10 Kelvin, which results in 9,907 cubic meters per hour. Breaking that down further, each module handles a flow of 1,651 cubic meters per hour, and each cooling distribution unit, or CDU, manages 198 cubic meters per hour at 2.3 megawatts and with a 10 Kelvin temperature difference. These figures highlight the precise control required to ensure efficient cooling performance and maintain optimal operating conditions within the data center. Understanding these flow checkpoints is crucial for effectively managing the thermal environment and ensuring system reliability. This slide covers a facility water flow checkpoint as part of our training concept package, specifically focused on the Badham Coastal Data Center. It involves key water supply systems like SWRO desalination, direct liquid cooling, and cooling tower integration. One of the key points here is the calculation of direct heat to facility water, which comes out to 118.7 megawatts after applying correction factor. This heat load determines a volume flow rate required to effectively manage cooling. Using the formula provided, the total flow volume calculates to about 12,756 cubic meters per hour. Breaking it down further, each module within the system handles around 2,126 cubic meters per hour, ensuring efficient distribution and cooling capacity across the facility. This detailed checkpoint is critical for engineers to understand flow requirements and design considerations within the integrated cooling systems. Here in Appendix E, we have the chiller condenser heat checkpoint, which serves as a detailed training note specifically designed for engineers. This section is part of our broader training concept package focused on the Badham Coastal Data Center's water supply system, including SWRO desalination, direct liquid cooling, and the integration of cooling towers. Let's focus on the key points presented. First, the compressor work, WOMP, is calculated by dividing 28.8 by 7.0, resulting in 4.1 megawatts. Next, the total condenser heat load, COND, is the sum of 28.8 and 4.1, which equals 32.9 megawatts. Finally, using these values, the condenser water flow rate is determined as 3,538 cubic meters per hour, calculated from the product of 32,914 and 0.86, divided by 8. These calculations are essential for understanding the cooling requirements and ensuring the chiller system operates efficiently within the data center environment. Here in Appendix F, we focus on the total tower heat checkpoint, which is a crucial aspect for our engineering team's training. This section is part of our comprehensive training concept package that covers multiple components, including the Batum Coastal Data Center's water supply, SWRO desalination, direct liquid cooling, and how the cooling tower integrates into the system. Now let's break down the key points. The total tower heat is calculated as 118.7 plus 32.9, which gives us 151.6 megawatts. This value is essential because it represents the amount of heat the cooling tower needs to dissipate. Next, we have the tower water flow rate. Using the formula provided, where we multiply the total heat by 0.86 and then divide by 8, we obtain a flow rate of approximately 16,297 cubic meters per hour. This flow rate is critical, as it serves as the input for open, closed, and hybrid water balance calculations, ensuring the entire cooling system operates efficiently and effectively. Understanding these calculations allows engineers to maintain optimal thermal management in the data center environment. Here we have the appendix section focusing on the open tower water checkpoint, which is an essential formula review for engineering training. This training module covers the integration of Batum's coastal data center water supply, including seawater reverse osmosis desalination, direct liquid cooling, and cooling tower systems. Let's highlight the key calculations here. First, E represents the evaporation rate, calculated as Q times 3,600 divided by the product of density and latent heat of vaporization, giving us about 223.7 cubic meters per hour. This value is critical for understanding water loss through evaporation. Next, the recirculation flow, labeled C, is derived by multiplying Q by 3.6 and divided by the product of specific heat capacity and the temperature difference. The result is approximately 16,297.2 cubic meters per hour, indicating how much water is cycled to the cooling system. Then blowdown BD is calculated by dividing evaporation E by the cycles of concentration minus 1, here resulting in 44.7 cubic meters per hour. This represents the water discharged to control mineral buildup. Drift loss, a small fraction of the recirculation flow at 0.001%, equals about 0.163 cubic meters per hour, accounting for water droplets carried away with the exhaust air. Finally, the total makeup water needed is the sum of evaporation, blowdown, and drift, which comes to 268.6 cubic meters per hour, or roughly 6,446 cubic meters daily. This is vital for ensuring continuous operation without dehydration of the system. This page serves as a handy formula reference during our engineering workshops, enabling precise calculations essential for maintaining efficient and sustainable cooling tower operations. This appendix provides a detailed formula checkpoint specifically for closed tower water systems, which is an important part of our engineering training package. It integrates key concepts related to Batum Coastal Data Center's water supply, seawater reverse osmosis desalination, direct liquid cooling, and how the cooling tower fits into this system. Let's go through the key points. First, we use the same heat rejection basis as the open wet system, which is 151.6 megawatts. Unlike some assumptions, there's no generic 1 to 2% heat penalty added for evaporation here, because the effect of the coil is accounted for in the equipment's sizing, approach temperature, and fan selection. When it comes to evaporation, the rate, represented as E, is 223.7 cubic meters per hour, identical to the open system at the same heat duty. The blowdown rate, calculated as E divided by the cycles of concentration minus 1, is 44.7 cubic meters per hour. Drift losses are minimized in this closed system, with a very low rate of only 0.0005% or 0.081 cubic meters per hour. Finally, the makeup water requirement totals 268.5 cubic meters per hour, which translates to about 6,444 cubic meters per day. This page is really useful as a formula check during training workshops to ensure our engineering calculations are aligned and accurate, especially when dealing with closed tower water systems in a complex cooling and desalination environment. This appendix section focuses on the hybrid tower water checkpoint, which is a detailed formula checkpoint designed specifically for engineering training. It is part of the broader training concept package related to the Batum Coastal Data Center's water supply system, including seawater reverse osmosis desalination, direct liquid cooling, and cooling tower integration. Key points to note here include the baseline all-wet closed system flow rate, which is 268.5 cubic meters per hour, or about 6,444 cubic meters per day. The optimized wet fraction is set at 45%, resulting in a makeup water volume of approximately 120.8 cubic meters per hour, or 2,900 cubic meters daily. A more conservative estimate uses a 65% wet fraction, leading to a higher makeup flow of 174.5 cubic meters per hour, translating to 4,188 cubic meters per day. In any case, the contingency plan still accounts for the full all-wet flow rate of 6,444 cubic meters per day. It's critical to emphasize that the final wet fraction value should be validated through detailed hourly climate and control simulations to ensure accuracy and system reliability. This page serves as a practical formula check during engineering workshops, helping trainers and engineers maintain precision in their calculations related to water makeup in the hybrid cooling tower system. This appendix serves as a detailed formula checkpoint designed to support engineering training, specifically focusing on the seawater reverse osmosis, or SWRO, process for the Batum Coastal Data Center water supply system. The training package covers several critical elements, including SWRO desalination, direct liquid cooling, and integration with cooling towers. Here are the key points to keep in mind. First, the open wet SWRO net water flow is calculated as 6,446 cubic meters per day, multiplied by a factor 1.10, which results in 7,091 cubic meters per day. Similarly, the closed wet SWRO net flow is 6,444 times 1.10, giving us 7,089 cubic meters per day. For a hybrid conservative SWRO net, the base is 4,188 multiplied by 1.10, equaling 4,608 cubic meters per day. Next, the reverse osmosis feed flow is determined by dividing the net water flow by the recovery rate of 42%. The brine flow, which is a concentrated reject stream, is then calculated as the difference between the RO feed and the net flow. Finally, the number of trains required is calculated based on a capacity of 1,500 cubic meters per day per train, with an N+1 configuration to ensure redundancy and reliability. This page is intended as a quick formula reference during engineering workshops to keep calculations consistent and accurate. This slide presents the key points from Appendix K, focusing on the Water Usage Effectiveness, or WUE, checkpoint for the Batum Coastal Data Center. The detailed training notes here are designed specifically for engineers and cover several important concepts, including water supply management, SWRO desalination, direct liquid cooling, and cooling tower integration. One critical figure to note is the peak IT energy consumption, which is 144 megawatts running continuously for 24 hours, totaling 3,456 megawatt hours per day. Using this baseline, we see the open-wet WE ratio is 1.87 cubic meters of water per megawatt hour, reflecting the water intensity without optimization. When applying a hybrid optimized approach, this number drops significantly to 0.84 cubic meters per megawatt hour, showing substantial water savings through integrated cooling and desalination techniques. The hybrid conservative scenario sits in between, at 1.21 cubic meters per megawatt hour, balancing water use efficiency with operational conservatism. These metrics are crucial for understanding how different strategies impact overall water consumption and efficiency in large-scale data center operations. Here in Appendix L, we focus on the Tier 3 water checklist, which serves as a detailed training guide for engineers. This training concept package is specifically designed around the Batum Coastal Data Center's water supply system. It covers crucial elements such as SWRO desalination, direct liquid cooling, and the integration of cooling towers. The key points to understand include the use of N+1 capacity components, ensuring redundancy and reliability. Additionally, There should be multiple maintainable distribution paths or sectionalized headers, allowing for flexible and reliable water flow management. Most importantly, no single planned maintenance activity should ever disrupt critical IT cooling functions. This ensures continuous operation and protects the data center's uptime. Here in Appendix M, we focus on the LEED and green mark documentation checklist, which is essential for ensuring our project meets sustainability standards. This section serves as a detailed training guide specifically designed for engineers to navigate the documentation requirements effectively. The training concept package covers critical topics related to Batum Coastal Data Center's water supply system. This includes seawater reverse osmosis, or SWRO desalination, which is an alternate water source, as well as the integration of direct liquid cooling and traditional cooling towers. Some of the key points to keep in mind are the installation and monitoring of permanent water meters, maintaining accurate logs for cooling tower makeup water and blowdown, and using water use efficiency calculation sheets alongside a monthly dashboard for ongoing performance tracking. Additionally, it's important to have a clear alternative water source narrative specifically addressing the SWRO system to support our sustainability goals. This appendix is designed to help engineers understand and document these aspects thoroughly and consistently. On this slide, we have the Appendix N section, which focuses on design review questions. It's meant to serve as a detailed training note for engineers to consider important aspects of the Batum Coastal Data Center project. The training concept package covers several critical areas, including the water supply, seawater reverse osmosis desalination, direct liquid cooling, and the integration of the cooling tower. Now, let's highlight the key points here. First, we need to ask if the selected cooling tower option meets the water use efficiency target. This ensures that the design is sustainable and efficient in terms of water consumption. Second, we must determine if an all-wet contingency is necessary for the hybrid cooling design, which affects how the system manages different cooling scenarios. Lastly, it's crucial to verify that every critical water component can be maintained without interrupting IT cooling operations. This ensures continuous system reliability and uptime for the data center. These questions aim to guide engineers through a thorough review process, ensuring the design is both effective and resilient. Here we focus on the Batum Data Center's water supply and liquid cooling strategy. Key components include SWRO desalination, which provides a reliable source of fresh water, direct-to-chip cooling distribution units that enhance cooling efficiency, and using cooling tower makeup water effectively. Water usage efficiency, or WUE, is a critical metric here, along with ensuring the data center meets Tier 3 readiness standards for reliability and redundancy. Our recommended next step is to run a detailed hourly weather-bin model for Batum. This model will compare closed wet cooling systems versus hybrid closed adiabatic towers to determine the most efficient and resilient approach. After this, we can finalize the seawater reverse osmosis system's normal and contingency sizing, aligning with the chosen water usage efficiency targets and resilience philosophy. Finally, there's a training concept package designed to cover all these aspects in depth. This includes a water supply for the Coastal Batum Data Center, how SWRO desalination integrates with direct liquid cooling, and the overall role of cooling tower integration to optimize performance and sustainability.